Imagine a colossal invisible force at the galaxy's heart, controlling its existence. This hidden conductor is none other than a supermassive black hole. Although they're often portrayed as chaotic, all-consuming monsters, these giants play a crucial role in the life cycle of galaxies. At the center of most large galaxies is a supermassive black hole whose gravitational pull is so strong that not even light can escape it. However, they actually do more than just absorb matter. They act as the heart and lungs of their galaxies, breathing life into the celestial environment in ways that are only beginning to be understood. Recent research shows that the jets of gas and radiation ejected from the poles of supermassive black holes are akin to the airways that feed our lungs. These jets create shock waves that oscillate, much like the thoracic diaphragm in our chest cavities, which moves to inflate and deflate our lungs. This respiratory system helps regulate the growth of galaxies, preventing them from getting too big and ensuring a delicate balance in the cosmic ecosystem. A simulation shows how a galaxy's heart and lungs in the form of gas plumes from a central supermassive black hole can prolong its life. If these supermassive black holes did not act as galactic regulators, the universe would be filled with zombie galaxies, huge clusters of dead or dying stars. The shock waves generated by black hole jets can prevent star formation by heating the surrounding gas, preventing it from cooling and condensing into new stars. This process may seem destructive, but it's necessary to maintain the health and longevity of galaxies. Today, we'll try to understand the mysterious nature of supermassive black holes, learn the profound impact they have on the universe, and by the end, we'll realize that even in the darkest corners of the cosmos, there is a heartbeat that connects us all. To fully understand the impact of black holes on galaxies, we need to understand their formation, types, and some key discoveries. Black holes can form in two main ways. The most common way is associated with the death of massive stars. When a star with a mass of about 8 to 10 times that of our Sun exhausts its nuclear fuel, a catastrophic explosion known as a supernova occurs. The core collapses under its own gravity, forming a stellar mass black hole. Such black holes usually have a mass several times that of the Sun. Another way is the direct collapse of massive gas clouds, which completely bypasses the star formation stage. This process can lead to the formation of black holes with masses from thousands to hundreds of thousands of solar masses. Such direct collapses are thought to have occurred in the early universe and were the seeds of the supermassive black holes we see today. The concept of black holes was first predicted by Carl Schwarzschild in 1915 as an exact solution to the equations of Einstein's general theory of relativity. These equations describe how matter forms the fabric of space and time. Schwarzschild's solution allowed us to discover regions where gravity is so strong that nothing, not even light, can escape it. The first black hole confirmed by observations was Cygnus X1. Discovered in 1964, this stellar mass black hole in the Milky Way was identified by X-ray emission that was caused by the accretion of material from a companion star. This discovery was the first convincing evidence that black holes are not just theoretical constructs, but real objects in the universe. Scientists have determined that a black hole consists of three main regions: the event horizon, the photon sphere, and the singularity. The event horizon is the boundary beyond which nothing can go once within its limits. The photon sphere is a region where gravity is so strong that light particles are forced to orbit. In the center, there is a singularity, a point of infinite density where the laws of physics known to us are destroyed. Black holes come in a variety of sizes. Stellar mass black holes are formed from collapsing stars and have masses several times that of the Sun. Supermassive black holes, located at the center of most galaxies, have masses ranging from millions to billions of solar masses. Intermediate mass black holes, which are less common, fall between these two categories and have masses between 100 and 100,000 solar masses. The 2019 Event Horizon Telescope collaboration has captured the first ever image of a black hole located in the galaxy M87. In this historic image, the black hole's shadow can be seen against a glowing accretion disk. The observation provided direct visual confirmation of theories about black holes and opened new possibilities for studying these mysterious objects. One of the most common and debated questions about black holes lately is whether they die. According to Stephen Hawking's theory, black holes can slowly evaporate over time through a process known as Hawking radiation. This occurs when pairs of virtual particles form near the event horizon, one falling into the black hole and the other flying out. Over an incredibly long period, this trickle of ejected particles can cause the black hole to lose mass and eventually vaporize. Although black holes are portrayed in science fiction, they're not cosmic vacuum cleaners that indiscriminately suck up everything around them. To hit them, objects must come incredibly close to the event horizon. In addition, although black holes have been proposed as potential wormholes or portals to other universes, these ideas remain speculative and are not supported by any observational data. Scientists estimate that the Milky Way alone contains more than 100 million black holes. Understanding the basics of black holes, how they form, their different types, and key discoveries lays a solid foundation for studying their profound impact on galaxies and the entire universe. So, although supermassive black holes are invisible, their presence is felt due to the enormous gravitational forces they exert on their surroundings. But how do these colossal formations arise, and what are their defining characteristics? Theoretically, a black hole is formed when a significant amount of matter is compressed into an incredibly small space, creating a gravitational field so powerful that it cannot escape. This concept, once considered too fanciful to be real, is now an accepted reality. Black holes, especially supermassive black holes, are scattered throughout the universe, and their number may be in the billions. Supermassive black holes with masses millions or billions of times that of the Sun are detected due to their gravitational influence on nearby stars. These stars orbit around the black hole much faster than they would around a normal object of similar size. By measuring these orbital velocities, astronomers can estimate the mass of the black hole. For example, the black hole at the center of our Milky Way, Sagittarius A, has a mass of about 4 million solar masses. Some supermassive black holes exceed even Sagittarius A. The dwarf galaxy Leo 1 is home to a black hole with a mass of about 3 million solar masses. In the neighboring elliptical galaxy Centaurus A, there is another black hole with a staggering mass of 55 million solar masses. And even more colossal is a black hole in the Abell 2261 galaxy cluster, estimated to have a mass of about 100 billion solar masses, although its exact location remains unspecified. These black holes, especially in active galaxies, behave differently. Surrounded by an accretion disk of rapidly spinning gas and dust, they can emit huge amounts of energy, sometimes outshining their entire galaxy. This very process was famously captured by the Event Horizon Telescope in 2019, when it imaged the accretion disk around the supermassive black hole in Messier 87, revealing the ominous shadow of a black hole with a mass of 6.5 billion solar masses. The formation of these supermassive black holes is the subject of intense study and speculation. Unlike the vacuum cleaners of science fiction stories, real black holes attract matter by gravity rather than by active suction. This gravitational attraction becomes unusually strong at close distances, but at greater distances, it behaves like the attraction of any other object of similar mass. According to one theory, The oldest supermassive black holes formed almost immediately by the gravitational collapse of massive gas clouds, containing as much matter as millions of stars. This direct collapse model suggests that such black holes could have formed in as little as 150 million years, a blink of an eye by cosmic standards. According to another hypothesis, primordial black holes born under the stressful conditions of the Big Bang served as seeds for subsequent growth. By studying these colossal formations, we gain insight into the fundamental processes that shape galaxies and, by extension, the universe itself. But what happens when two galaxies collide? It's not just a dramatic cosmic event, it's a transformational process that changes the very fabric of the universe. At the center of these galactic collisions are the same supermassive black holes, and their interactions produce some of the most energetic phenomena known. When galaxies approach each other, their central supermassive black holes begin to interact gravitationally, spiraling toward an inevitable merger. This process is not silent. It sets in motion vast amounts of ambient gas and dust, creating a turbulent environment ripe for extraordinary phenomena. Physicists have modeled these colossal mergers and found that as black holes spiral closer together, they can produce incredibly energetic jets of electromagnetic radiation. They fly out along the axis of rotation much more powerfully than those typically observed around isolated black holes. The cosmic show begins even before the black holes fully merge, giving astronomers a potential warning of these events. When these supermassive black holes finally collide, their jets combine into single high-energy bursts. These may be accompanied by less directional bursts, increasing the chances of detection. The merger process sets the surrounding plasma in motion, causing powerful jets that can theoretically be observed from billions of light years away. The detection of these cosmic events is not just exciting, it provides a unique opportunity to test the limits of Einstein's general theory of relativity under extreme conditions. The observation of these mergers can either strengthen the current understanding of gravity or open up new physics, potentially leading to alternative theories. Future missions such as the Laser Interferometer Space Antenna, or simply LISA, promise to expand our ability to pinpoint these mergers. LISA, a joint effort between NASA and the European Space Agency, will orbit the Sun and detect gravitational waves emitted by such mergers. Combining gravitational wave data with electromagnetic observations will allow precise localization and detailed study of these energetic events. Until such advanced instruments become operational, astronomers rely on existing observatories to detect electromagnetic jets. They provide a dynamic view of galaxy evolution, demonstrating how such mergers can dramatically change the structure and behavior of galaxies. But let's take a closer look at Sagittarius A, which is 4.3 million times the mass of the Sun. In mid-spring of this year, the giant of our galaxy revealed new secrets, thanks to the advanced observations of the Event Horizon Telescope. For the first time, astronomers have recorded polarized light around Sagittarius A, providing new insights into the magnetic fields surrounding this black hole. Polarized light is crucial to understanding these fields because it shows how light waves are oriented and allows us to understand the properties of the gas and the mechanisms at work in powering the black hole. Interestingly, the magnetic fields around Sagittarius A are strikingly similar to those observed around the much larger black hole in the galaxy Messier 87, which has a mass of 6.5 billion times that of our Sun. This similarity suggests that strong organized magnetic fields may be a common feature of all black holes, regardless of their size. The presence of such magnetic fields makes the possibility that Sagittarius A may contain a hidden jet intriguing. In other black holes, these fields drive powerful streams of matter. Although Sagittarius A appears relatively quiet, consuming a minimum of matter, The similar structure of its magnetic field hints at the possibility of a weak jettison that has yet to be observed. This new image of a black hole at the center of the Milky Way tells us that there are strong, swirling, and ordered magnetic fields near the black hole, explains Sarah Issa Un, study co-leader and NASA Hubble Fellowship Program Einstein Fellow at the Center for Astrophysics at Harvard and Smithsonian. These fields are crucial to how black holes interact with the gas and matter around them. It was the EHT, an array of telescopes around the world, that made these groundbreaking observations possible. By combining data from multiple telescopes, the EHT forms an Earth-sized virtual telescope capable of capturing unprecedented detail of black holes. Although Sagittarius A is closer to Earth, it presents a unique challenge because of its smaller size. The material swirling around it moves quickly, making it difficult to get clear images. In contrast, in the larger M87, the material moves more slowly, making it easier to observe. Overcoming these difficulties has provided invaluable data for comparing black holes at opposite ends of the mass spectrum. The observed similarity in the magnetic fields between Sagittarius A and Messier 87 suggests that the central black hole of our galaxy may possess a hidden jet. If such a jet exists, it would provide new insights into the behavior and evolution of black holes and the galaxies in which they reside. The observation of this jet would be a great discovery, linking Sagittarius A to the energetic processes that form galaxies. The discovery of such a jet will greatly expand our understanding of how black holes affect their surroundings. Jets can expel gas and dust, affecting star formation and the overall evolution of galaxies. By comparing different black holes, astronomers will be able to identify the universal principles that govern these mysterious objects. Studying our own supermassive black hole allows us to root these abstract concepts in a familiar context, bringing distant space closer to home. The influence of supermassive black holes extends far beyond their gravitational effects. Relativistic jets can have a dramatic effect on the formation and evolution of galaxies, affecting everything from star formation to the distribution of gas and dust. A striking example of the influence of black hole jets is the Teacup Galaxy, located at a distance of about 1.3 billion light-years from Earth. The Teacup Galaxy got its name because of its peculiar handle structure, which was formed due to the activity of a relativistic jet from its central supermassive black hole. This galaxy is a vivid example of how even low-powered jets can significantly affect the environment. Even in the case of radio-quiet galaxies, jets can redistribute and disrupt the surrounding gas, and this will have an impact on the galaxy's ability to form new stars. Recent observations with the Atacama Large Millimeter Array have shown that jets in the Teacup Galaxy, although relatively weak, move, heat, and accelerate the galaxy's gas. Even in the case of radio-molten galaxies, jets can redistribute and disrupt the surrounding gas, and this affects the galaxy's ability to form new stars, explains Cristina Raus Almeida, an astronomer at the Instituto de Astrofísica de Canarias. The effects of these jets do not always occur head-on. The study found that the most significant effects in the Teacup Galaxy occur perpendicular to the direction of the jets. This lateral turbulence is caused by shock waves generated by the jet bubble, which heats and inflates the gas. These interactions can prevent star formation by preventing the gas from cooling and collapsing into new stars. While strong jets can heat the gas in galaxies to such an extent that they slow its growth, preventing the formation of new stars, weaker jets, such as in radio-quiet galaxies, also play an important role. These jets can still stir up the gas in a galaxy, causing it to move and redistribute. Such activity can lead to the formation of new structures within the galaxy and affect its long-term evolution. Understanding the influence of these jets allows astronomers to piece together the complex puzzle of galaxy formation. Supermassive black holes are an integral part of the life cycle of galaxies, from the dramatic changes caused by powerful jets to the more subtle but significant effects of weak ones. Stay tuned to explore together the forces that shape our universe. Our universe hides a mystery that's long captivated the human mind. A question that bridges the gap between the known and the unknown, the simple and the complex. Here on Earth, life thrives in a continuous movement of order and chaos. Every form of life is evidence of a hidden order, a pattern woven into the very fabric of existence, from the smallest microorganisms to the largest mammals. But what if the complexity of life, the very essence of our existence, could be explained not only through the lens of biology, but also through a mathematical framework? This is the territory of assembly theory, a groundbreaking concept that transcends traditional science. It's a journey into a world where math and biology converge to reveal the hidden architecture of life. Imagine a universe in which the secrets of life, from the simplest molecule to the most complex organism, are encoded in mathematical language and are waiting to be decoded, where the line between living and non-living is blurred, giving birth to new possibilities and new understanding. Let's explore how this revolutionary idea is changing our perception of life, evolution, and the cosmos itself. And maybe we can even get closer to answering the ultimate question: what is the true nature of life in the universe? Since the dawn of civilization, mathematics has been the language of the universe, a tool for deciphering the mysteries of nature. But how does this language of numbers and equations relate to understanding the very essence of life? At its core, assembly theory offers a simple but profound idea. The complexity of life can be measured and understood through a mathematical prism. Think of life as a jigsaw puzzle, where each piece represents a molecular building block. Assembly theory seeks to show how these pieces come together step by step to form the complex structures that define living organisms. Each step in this assembly process represents a leap of complexity, from simple atoms to complex proteins. The theory introduces the concept of the assembly index. The assembly index, the cornerstone of this theory, measures the number of steps required to build a biological structure. It's a numerical value that captures the essence of complexity by quantifying the immeasurable. But how does the standard model of physics fit into this? This standard model theory of physics describes the fundamental particles and forces that govern our universe. It seems completely separate from the complexities of biology. However, assembly theory bridges this gap. In the field of assembly theory, the standard model lays the foundation for understanding forces and interactions. It's a bridge between the microscopic world of quarks and leptons and the macroscopic world of living things. Another important element of the theory is the concept of studying dynamical systems, phase space. This is a mathematical concept used to describe all possible states of a system. In the context of assembly theory, phase space allows us to map the path of the assembly of life. From a single point representing the simplest form of life, phase space expands, branching out into almost infinite possibilities, each pathway representing a different route that life can take. In this limitless mathematical landscape, the paths of evolution and its complexities unfold. This mathematical framework gives us a new perspective on the complexity of life. It's not just about the particles and forces described by the standard model, but how these elements combine and interact over time to create the diverse pattern of life we see around us. This is where the chaos of random molecular interactions gives way to the order of living structures. So let's ask ourselves this question: are the complexities of life simply the product of chance, or is there a deeper cause? Let us consider two sharply contrasting concepts: complexity and entropy. Entropy, a measure of disorder and randomness, seems to be at odds with the complexity we observe in life. How do these opposing forces coexist in the natural world? It's here that assembly theory offers a revolutionary perspective. So, central to assembly theory is the assembly index, a revolutionary tool designed to measure the complexity of life. Think of it as a cosmic ruler, measuring the steps required to assemble a biological structure from its simplest components. Imagine a single molecule as the starting point on this scale. As you move up the scale, each step represents a more complex assembly, from molecules to cells and beyond. The higher the index, the greater the complexity, and the less likely it is that the structure could have arisen by chance. Now let's delve into the interaction between entropy and complexity. Entropy, a concept rooted in thermodynamics, suggests that systems naturally tend toward disorder. However, life defies this tendency, evolving from simple origins to a variety of forms combined into the complex ordered structures we see today. How does assembly theory resolve this apparent contradiction? It suggests that life is inherently a process of overcoming entropy. Through the lens of the assembly index, we see the complexity of life is not a challenge to entropy, but a journey through it. Consider the early Earth, a primordial soup of simple molecules. Over millennia, driven by the laws of physics and chemistry, these molecules began to assemble into more complex structures. Each step along the way marked a victory over entropy, a step toward greater complexity in life. Rethinking evolution through assembly theory, we see it not as a mere biological process, but as a mathematical inevitability. The emergence and evolution of life became a story of increasing complexity, a story written in the language of mathematics. Let us now turn to a very trivial question, but one that shines in a new light. Are we alone? The search for extraterrestrial life has captivated our imagination for centuries. Now, thanks to assembly theory, we have a new tool in this cosmic quest. Assembly theory offers a unique approach to detecting alien life. It's not about scanning the sky for radio signals or analyzing light spectra for the presence of oxygen. Instead, it's about understanding the complexity of molecules and structures that may indicate life. Imagine scanning the atmosphere of a distant exoplanet or the surface of a moon in our solar system. Using assembly theory, we could analyze the molecular complexity of the samples in search of patterns that indicate the presence of life. The higher assembly index, the more likely it is that these molecules are the result of life rather than random processes. However, the road to discovering alien life is full of challenges and limitations. One of the biggest obstacles is our understanding of life itself. Our definition of life is based on what we know. Life on Earth. What if it doesn't meet our biochemical standards? Another problem is the vastness of space. The universe is vast, and our ability to explore it is limited by current technology. Even with the most sophisticated telescopes and probes, we can only analyze a tiny fraction of the cosmos. Moreover, assembly theory, while powerful, is still in its infancy. It's a new approach, and its application to the search for extraterrestrial life is uncharted territory. There are questions about its applicability and accuracy in different environments, especially those that are very different from terrestrial environments. Despite these problems, the potential of assembly theory in the search for alien life is enormous. It could redefine our understanding of life in the universe, opening new doors in astrobiology. So assembly theory offers a new way of looking at life, not just as a biological phenomenon, but as an emergent property of cosmic complexity. Imagine the early days of our planet, a world in motion, a crucible for the chemistry of life. Here in this chaotic environment, simple molecules began the journey of assembly. a process governed by the laws of physics and chemistry but leading to something much deeper. Life, according to assembly theory, emerges when these molecular structures reach a level of complexity that allows them to store and reproduce information. This is where chemical memory, a crucial step in the evolution of life, comes into play. Chemical memory is the ability of certain molecular structures to retain structure. In other words, we can say this is the blueprint for life. In the world of assembly theory, this is where reproducibility becomes key. The ability to reproduce these patterns, to pass them on from generation to generation, is what drives the evolution of life. From the simplest RNA molecules in the primordial soup to the vast diversity of life we see today, each step in this evolutionary journey has been a step up the assembly index. Each increase in complexity represents a triumph over the entropy that governs the universe. But the story of the origin and evolution of life is not just a story of increasing complexity. It's also a story of resilience and adaptability. Life has found a way to thrive in the most extreme environments, from the depths of the ocean to the fringes of space. In the realm of scientific discovery, every new theory is scrutinized and debated. Assembly theory, a concept that promises to revolutionize our understanding of life and complexity, now stands at a crossroads being questioned by critical voices such as Dr. Hector Zenel. The critique presented by Zenel raises fundamental questions about the future evolution of assembly theory. Covering an impressive 18,000 words, the article will require time and thought, taking approximately 1 to 2 hours of dedicated reading. This is not a cursory look at the topic, but a deep dive into the heart of the scientific debate. For those who are interested, we leave a link in the description to both articles, the study and the counter-arguments to it. Looking to the future, the role of assembly theory in scientific research remains uncertain. Will it be able to adapt and overcome these challenges? Or will it remain a footnote in the history of science? Despite the disagreements, one thing is clear. The debates surrounding assembly theory have initiated a conversation on the nature of scientific discovery. They emphasize the need for transparency, rigor, and humility in pursuing knowledge. In the end, the impact of assembly theory on future research may not lie in its specific claims, but in the lessons it teaches us about the scientific process. As we explore the mysteries of life in the universe, such theories will come and go. But the quest for understanding, the quest to unlock the mysteries of our existence, will always remain at the center of the interest of scientific research. Supernovae are not just amazing events in the universe. They're vital cosmic phenomena that shape and create galaxies. These powerful explosions occur at the end of a massive star's life cycle, ejecting elements into space from which new stars, planets, and even life itself are formed. In essence, supernovae serve as both destroyers and creators of galaxies. In the study of supernovae, imagery plays a crucial role in understanding these powerful explosions. Over the years, advances in imaging technology have allowed astronomers to capture spectacular views of supernovae at different stages, revealing intricate details of their structure and the elements they eject into space. The story of Betelgeuse, a red supergiant star, is a prime example of how images help us understand the behavior of supernovae. Betelgeuse has recently attracted a lot of attention due to its sudden fades and increases in brightness. This variability has led to speculation of its imminent explosion, sparking widespread interest. The appearance of a dust cloud around the star, observed in telescopes and captured on images, was initially taken as a precursor to a supernova. However, later it began to be considered as a natural phenomena in the life cycle of red supergiants. So why did scientists initially hypothesize the possibility that this star would be the next observed supernova? This red supergiant occupies a prominent place in the constellation of Orion, perched on its shoulder, and is visible to the observer even to the naked eye. Let's take a look at the life cycle of Betelgeuse, an intriguing journey that will show the evolution of the star from its birth to its current state as a massive, pulsating giant nearing the end of its life. Betelgeuse began its existence as a massive star burning hydrogen in its core, like many others. However, because of its large mass, it evolved rapidly, entering successive phases of nuclear fusion. The significant mass of the star distinguished its evolutionary path from the evolution of smaller stars, such as our Sun. While the Sun is currently a stable main-sequence star slowly converting hydrogen into helium, Betelgeuse, due to its much larger mass, more quickly depleted its hydrogen reserves and evolved into a red supergiant. The key difference between Betelgeuse and our Sun is their masses. Betelgeuse, which has about 15 to 20 times the mass of the Sun, experiences higher pressure and temperature in its core, which accelerates nuclear fusion. Intense fusion causes Betelgeuse to burn its fuel rapidly, resulting in an unstable structure and significant brightness fluctuations. In contrast, the Sun's lower mass allows it to remain stable for billions of years, with a much longer and more stable hydrogen-burning phase. As Betelgeuse aged, it entered successive phases of nuclear fusion, gradually burning off elements heavier than hydrogen. Internal pressure caused the star to begin to swell, transforming it from a main-sequence star into a red supergiant. This stage is characterized by Betelgeuse's enormous size and variability in brightness. The star expands and contracts as it undergoes complex nuclear processes. Recent observations have suggested that Betelgeuse may be on the verge of a supernova. The star's dimming in 2019, followed by an unexpected increase in brightness, has led scientists to speculate that it may be approaching the final stage of its life. These changes in brightness are thought to be related to internal processes, possibly signaling the beginning of core collapse. The star's pulsations, with cycles of 185, 230, 420, and 2200 days, were analyzed to understand its internal dynamics. The longest cycle of 2200 days is particularly intriguing because it may represent Betelgeuse's fundamental pulsation mode, indicating its advanced stage of evolution. These observations, along with recent telescopic findings, suggest that Betelgeuse may be entering a phase of carbon combustion that precedes a supernova explosion. But what are the complex nuclear processes that dictate when a star's life must come to an end? At the center of a massive star like Betelgeuse, nuclear fusion turns hydrogen into helium, releasing enormous energy. As the star ages, heavier and heavier elements fuse to form bulb-like layers. Eventually, the core is filled with iron, which cannot release energy during the fusion process, leading to gravitational collapse. As the core collapses, a runaway reaction is triggered. In this process, the iron core collapses under enormous gravitational forces, reaching temperatures of billions of degrees. This leads to the rebound effect, where the core inflates and then explodes, creating a shockwave that rips the star apart. A supernova explosion releases an enormous amount of energy, briefly eclipsing an entire galaxy. The mechanics of this process involve a complex interplay between nuclear collapse, gravitational forces, and intense heating. The shockwave generated by the collapse of the core propagates outward, ejecting the outer layers of the star into space. Ancient astronomers have recorded these bright phenomena for thousands of years, sometimes describing them as guest stars, or new stars. The earliest recorded supernova observation dates back to 185 AD when Chinese astronomers observed guest stars, as they called them, that were visible for 8 months. Although rare, astronomers continue to study them to this day, especially when they lead to unusual phenomena such as gamma-ray bursts. Gamma-ray bursts, or GRBs, are intense bursts of gamma rays, usually associated with the collapse of massive stars or the merger of neutron stars. These bursts are some of the most energetic events in the universe, capable of releasing more energy in just a few seconds than the Sun will emit in its entire 10 billion-year lifetime. The discovery of the Boat GRB, also referred to as the brightest of all time, in October 2022, was a milestone in GRB observations, stunning astronomers with its unprecedented brightness and startling impact on Earth. The Boat GRB, officially designated GRB 221009A, was detected on October 9, 2022, and originated from a galaxy about 2.4 billion light-years away from Earth. The event was unusual not only in its brightness, but also in its duration. It lasted about 7 minutes, much longer than a typical gamma-ray burst. The burst was so powerful that it affected the Earth's ionosphere, temporarily disrupting radio communications and altering the ionization of the atmosphere. The relationship between supernovae and gamma-ray bursts is complex and fascinating. In some cases, the collapse of the core of a massive star can trigger a GRB, especially if the star is rapidly rotating and has a strong magnetic field. Such long GRBs often last more than 2 seconds and are often followed by a supernova explosion. Boat was notable not only for its brightness but also for providing insight into the formation of heavy elements. In April of this year, scientists studied this burst in detail, initially hoping that it might provide clues about the origin of elements heavier than iron, which are usually formed in supernova explosions or neutron star mergers. However, further analysis showed that GRBs do not produce these elements, leaving scientists even more puzzled and emphasizing the mysterious nature of such cosmic phenomena. To find out exactly what caused the flare, scientists used a variety of observational tools, including the James Webb Space Telescope. The exceptional brightness of the flare initially obscured its surroundings, making it difficult to observe the accompanying supernova or other objects in the host galaxy. It took several months before the brightness diminished enough to make detailed observations possible. As a result, a relatively undetectable supernova remnant was detected, which was surprising given the power of a gamma-ray burst. The Boat GRB also provided insight into the characteristics of gamma-ray bursts. The exceptional brightness and long duration of this event indicated that the GRB was very focused, with narrow jets pointing directly toward Earth. This narrow directivity likely contributed to the observed intense brightness, as gamma-ray bursts tend to be directional phenomena. The narrow burst jets were probably the result of a rapidly rotating star with a strong magnetic field that produced a powerful and focused flare. While Boat GRB has provided insight into gamma-ray bursts and supernovae, scientists continue to find answers to the mysteries of Betelgeuse. Recent research suggests that Betelgeuse's cycles of dimness and brightness are part of its natural behavior as a variable star. It turns out that, unlike our Sun, Betelgeuse is an extremely explosive and low-density plasma cloud that changes shape frequently. Created by scientists, simulation illustrates the behavior of Betelgeuse in time. Periods of brightness and dimness occur about every 400 days. And the longer cycle is about 2,000 days. Recent studies have tried to explain the Great Dimming phenomena that occurred in 2020, and observations from various telescopes over the past 15 years have provided much insight. observations at various frequencies, including microwaves and infrared, have allowed scientists to penetrate the layers of Betelgeuse and detect silicon monoxide, indicating the presence of a large dust cloud. This discovery disproved initial speculation that Betelgeuse was about to explode. Instead, it appears that internal activity within the star has caused the material to separate, forming a large gas cloud. The formation of a cold region beneath this cloud caused particles to condense, creating a dark cloud that obscured Betelgeuse from view from Earth. Further study of Betelgeuse's behavior revealed that the star experienced two shockwaves, one in 2018 and another 1 year later. These waves disrupted the surface, creating hot and cold spots, which was confirmed by Hubble Space Telescope ultraviolet imaging observations. The shockwaves and their aftermath disproved the initial assumption that Betelgeuse was close to a supernova, and instead showed that this behavior of the star is part of its natural life cycle. Betelgeuse's behavior is also characterized by its high rotation rate. Unlike typical red supergiants, which rotate slowly, Betelgeuse rotates at about 3 miles per second, which initially led researchers to think that it might have been a binary star that collided. However, recent research suggests that this rotational speed may be influenced by fast-moving convective cells inside the star, contradicting initial assumptions about its rotational behavior. Despite the unusual behavior, this research suggests that Betelgeuse is unlikely to become a supernova in our lifetime. The current state of the star is more like a variable red supergiant nearing the end of its life, but by no means approaching a supernova explosion. So finally we come to the very question that concerns all of us. How would such an explosion affect our home planet? The potential impact of a nearby supernova on Earth is a subject of speculation and concern. While a supernova is not expected to pose an immediate threat to our home, the explosion of a star within a few light years could affect Earth's atmosphere and potentially impact life. For example, the flare of the very same boat GRB was so intense that it significantly affected the Earth's ionosphere, altering atmospheric conditions and disrupting radio communications. The flash released a tremendous amount of energy that interacted with the Earth's atmosphere, causing a sudden increase in ionization. This increased ionization affected the ozone layer and triggered chemical reactions that scientists are still trying to understand. The GRB also disrupted radio signals, especially those used for communication and navigation. The energy released in the explosion was so great that it even blinded several satellites, demonstrating the enormous power of these cosmic phenomena. However, the burst itself was observed from a galaxy a whopping 2.4 billion light-years away. This event only emphasizes the need for further study of gamma-ray bursts to understand their impact on us, our planet, and the universe as a whole. In addition, supernova studies also contribute to our understanding of dark matter, dark energy, and the overall structure of the universe. Type 1a supernovae, which occur in binary star systems, are crucial for measuring cosmic distances and studying the expansion of the universe. These standard candles have helped astronomers detect the accelerating expansion of the universe, which in turn has provided the background for understanding dark energy. Supernovae are a key focus of future astronomy. Their explosive nature and transformative impact continues to fascinate scientists and inspire discovery. Well, while some people are frozen in anticipation of the Betelgeuse explosion on live internet feeds, we look forward to discoveries from missions such as the Vera Rubin Observatory and the European Space Agency's Euclid telescope, which will contribute to advancing our understanding of supernovae. As we look deeper into space, these stellar explosions will undoubtedly shape our understanding of the universe and our place in it. You've probably heard of dark matter, the elusive substance that makes up about 1/4 of the universe. That ghostly puppeteer is pulling the strings of the galaxy but never showing itself. But what if dark matter is just the tip of the cosmic iceberg? Imagine a universe where the scales of gravity tip in mysterious ways, where stars and binary systems, two stars orbiting a common center, defy the very laws established by Newton and Einstein. What if their equations are not the final word? Recent research suggests anomalies and deviations in the orbital dance of double stars that neither dark matter nor our current understanding of gravity can fully explain. So, are we on the cusp of a paradigm shift? Is our view of the cosmos not as stable as we thought? In cosmic ballet, stars are the prima donnas that catch our eye. But have you ever wondered how these celestial luminaries come into being? It all starts in the dark, cold corners of a nebula, a vast cloud of gas and dust. Gravity plays a key role here, pulling the particles closer and closer until they no longer resist gravity. They merge, triggering a nuclear fusion reaction that produces a star. However, the life of a star does not last forever. There comes a point when the nuclear fuel runs out, and the star faces its inevitable demise. For massive stars, this end is nothing short of spectacular. A supernova explosion that eclipses entire galaxies, if only for a short time. These supernovae are not just cosmic fireworks. They are the forges of the universe. It's in the crucible of these explosions that elements heavier than iron are created. So the gold in your jewelry, the calcium in your bones, it's all stardust. The remnants of a supernova explosion. But here's where the plot gets twisted. In a universe dominated by dark matter, these stars and their explosive deaths are part of a larger scene. Dark matter, with its gravitational pull, influences the formation of galaxies and the distribution of stars within them. Imagine two galaxies, one with dark matter and one without. In the galaxy with dark matter, the gravitational forces are so strong that they can cause bursts of star formation, leading to a higher number of supernovae. In these galaxies, stars form and die at an accelerated rate, creating a dynamic and ever-changing landscape. Recent studies have even quantified this relationship, showing a direct correlation between the amount of dark matter in a galaxy and the rate of star formation. But what if this correlation is not as simple as it seems? Enter MOND, Modified Newtonian Dynamics. This theory suggests that gravity behaves differently at very small accelerations. If MOND is correct, the high rate of star formation in dark matter-rich galaxies may have an alternative explanation. Double star systems, those cosmic pairs we discussed earlier, can serve as an ideal test laboratory for these theories. Their orbital dynamics can show whether Newtonian gravity persists or whether MOND offers a better explanation. As scientists delve deeper into the data, especially the treasure trove provided by the Gaia mission, we're getting closer to understanding the true nature of this galactic dance. In cosmic narratives, dark matter is often portrayed as a silent, mysterious entity that shapes galaxies but remains elusive. One of the most compelling theories attempting to solve this mystery is the cold dark matter model, or CDM. In the CDM model, dark matter is cold, which means that its particles move much slower than the speed of light. This slowness allows them to clump together to form the gravitational scaffolding on which galaxies are built. CDM-based computer modeling has been extremely successful in reconstructing the large-scale structure of the universe. It shows a cosmic network of galaxies connected by dark matter filaments that's very similar to what we observe. But, like any good story, there are unexpected plot twists. While CDM does an excellent job of explaining the grand architecture of the universe, it falters when we get closer to individual galaxies. Take, for example, the rotation curves of galaxies, the speed at which stars and gas rotate around the galactic center. According to Newtonian physics and the CDM model, this speed should drop sharply as we move away from the center. But observations tell a different story. The rotation curves remain surprisingly flat, suggesting that something else is involved here. Perhaps another kind of dark matter, or even a modification of gravity. And then there are dwarf galaxies, smaller satellites of larger galaxies like our Milky Way. The CDM model predicts many of these dwarf galaxies, but we just don't see as many as expected. These inconsistencies have led scientists to consider alternatives and question the very basis of the CDM model. Could it be incomplete, or are we missing an important piece of the cosmic puzzle? This is where MOND enters the scene again, offering a different set of equations that better explain these galactic features. It's like two different scripts of the same movie, each with its interpretation of the main character, dark matter. At check weighing, the scientific community is divided. Is the CDM the final theory that unifies our understanding of the universe, or is it just a stepping stone toward a more complete model? For centuries, Sir Isaac Newton's equations have been the foundation of our understanding of gravity. They have been tested, retested, and retested, and have stood the test of time. But what if there is more to the story? Introducing MOND, or Modified Newtonian Dynamics, a theory that dares to modify Newton's sacred equations. It suggests that gravity behaves differently at extremely low accelerations, such as at the outskirts of galaxies. The goal of MOND, conceived by physicist Mordecai Milgrom in the early 1980s, is to resolve some of the inconsistencies that have arisen in our observations of galaxies, especially those puzzling rotation curves we discussed earlier. You see, MOND fits the observed flat rotation curves of galaxies perfectly, without resorting to dark matter. It's as if MOND is saying, wait, maybe you don't need to invent a mysterious form of matter. Maybe you just need to adjust your equations. And it's not just about rotation curves. MOND has also managed to explain the dynamics of some galaxy clusters, and even the large-scale structure of the universe, without relying on the mysterious dark matter. But of course, no theory is without problems. While MOND succeeds in some areas, it faces difficulties in others, such as explaining the cosmic microwave background afterglow of the Big Bang. The cosmic microwave background, or CMB, is a snapshot of the universe just 380,000 years after the Big Bang. The CDM model, with its dark matter component, explains the features of the relic radiation well. MOND, however, has difficulties here. And let's not forget our celestial pairs, double star systems. Recent studies, some of which we've already discussed, have shown contradictory results when applying MOND to double stars. So what does that give us? Well, at the very least, a state of exciting uncertainty. As new data comes in, especially from the Gaia mission, MOND continues to be hotly debated. Is MOND the missing piece of the puzzle that will finally explain the anomalies we observe? Or is it a useful but ultimately flawed stepping stone towards a more complete theory? In a universe full of questions, sometimes the answers lie closer to home. Just 1.5 million kilometers from Earth orbits Gaia, a spacecraft that may hold the keys to some of the universe's most puzzling mysteries. Launched by the European Space Agency in 2013, Gaia is no ordinary telescope. It's It's a space cartographer mapping the positions, distances, and motions of more than 1 billion stars with unprecedented accuracy. Imagine having the coordinates of 1 billion stars at your fingertips. It's like Google Maps for the Milky Way, but with a staggering level of detail. One of Gaia's key techniques is parallax, an ancient method with a modern interpretation. By observing a star from 2 different points in its orbit, Gaia can triangulate the distance to the star with incredible accuracy. But Gaia is more than just a space explorer, it's a theory tester. Remember those controversial theories about gravity and dark matter? Gaia data can be used to put those theories under the microscope. Take, for example, double star systems. These systems are crucial for testing theories like MOND. Gaia's precise measurements of the positions and velocities of these stars can help us understand which theory is correct. And it's not just stars. Gaia also observes asteroids, planets, and even distant galaxies. Its data have been used to refine the Hubble constant, a key parameter that helps us understand the expansion rate of the universe. Measuring the Hubble constant with Gaia has added a new twist to the ongoing cosmic controversy. Different methods yielded slightly different values, and Gaia's data became an important piece of this cosmic puzzle. But the Gaia mission is not without its challenges. While the spacecraft provides a wealth of data, interpreting that data is a different story. The same Gaia data have been used to both support and refute theories such as CDM and MOND, leading to heated debates in the scientific community. It's like a high-resolution photograph where everyone sees something different. Is it a speck on the lens or a revolutionary discovery? Interpretation depends on sophisticated statistical methods and, of course, on our basic assumptions about the universe. There is nothing more fascinating than double stars. 2 stars locked in a gravitational embrace, orbiting each other in a delicate balance of attraction and repulsion. As we mentioned earlier, these dual systems are not just celestial spectacles, they are cosmic laboratories. Here, in the intricate ballet of their orbits, we can test our deepest theories about the nature of gravity itself. Double stars have been a cornerstone of astronomical research for centuries. They've helped us measure the mass of stars, understand stellar evolution, and even confirm Einstein's general theory of relativity. But in the context of our ongoing debate between cold, dark matter and modified Newtonian dynamics, double stars play an even more important role. Their orbital dynamics can reveal whether Newtonian gravity persists or whether MOND offers a better explanation. Recent studies have delved deeper into this question. Some studies, using data from the Gaia mission, have shown that double star systems behave as predicted by Newtonian gravity, casting doubt on the applicability of MOND. However, other studies tell a different story. They suggest that MOND is better suited for some double systems, especially those with large distances between them and weak gravitational attraction. Could it be that both theories are partially correct? Or are we missing a key piece of the puzzle? The scientific community is divided, and for good reason. The stakes are high. The behavior of double stars could either confirm our current theories or send us back to the drawing board in our quest to understand the universe. So, how do we weigh evidence? Meet Bayesian statistics, a mathematical framework that might just tip the scales. Named after Thomas Bayes, an 18th century statistician and theologian, Bayesian statistics offers a way to update our beliefs in light of new data. It's like a mathematical expression of the scientific method itself. Here's how it works. You start with a prior belief, or prior, which is your initial hypothesis. As new data becomes available, you update it before forming a posterior hypothesis, a revised hypothesis that better fits the actual data. In the context of our cosmic debate, be it cold dark matter, MOND, or something completely different, Bayesian statistics provides a rigorous way to assess which theory is more likely, given the observed data. For example, when analyzing double star systems, Bayesian methods can help quantify the probability that MOND, or Newtonian gravity, is the correct theory. It's not just about curve fitting, it's about estimating the weight of evidence. And it doesn't just apply to double stars. Bayesian statistics have been applied to a wide range of cosmic phenomena, from the distribution of dark matter in galaxy clusters to the rate of expansion of the universe. Nevertheless, Bayesian methods are not without critics. One of the most controversial points is the choice of a prior. How to choose the initial hypothesis in a way that does not distort the result. The choice of a prior can be controversial because it can affect the results. If your prior leans strongly towards one theory, a posterior may confirm that theory even if the other is equally true. As we grapple with these questions, Bayesian statistics remain a powerful tool in our analytical arsenal. It offers a way to make sense of complex spatial data, sift through the noise, and find the signal. The universe seems to refuse to reveal its secrets readily. Even as we gather more data, the debate about the true nature of gravity is intensifying. Hyun Che, an astronomer who recently hit the headlines, said, quote, "I was feeling like I was dreaming. It seemed so unreal. This is because my results did not match any previous results." Che's work stirred the pot by suggesting that when the gravitational acceleration of stars in certain double systems falls below a certain threshold, they're more consistent with MOND models than with the standard gravity model. But here's the rub. Che's findings contradict several previous studies. He mentions, quote, "One group has been claiming an anomaly for some time, but the anomaly seemed not to match well the predictions of existing modified gravity theories." This discrepancy in results is not just a glitch. It's a fundamental challenge to our understanding of the cosmos. It raises questions about the reliability of our models and the data we use to test them. So what does that give us? Well, at least a state of productive confusion. As Che concludes, quote, "Because the standard cosmology is based on general relativity, cosmology needs a major revision now." The debate is far from over. As we collect more data and refine our theories, the search for the ultimate truth about gravity and the universe continues. And in this quest, every anomaly, every contradictory result adds a new level of complexity and wonder. In the field of space exploration, the James Webb Space Telescope is a beacon of human ingenuity and curiosity. Its recent incursion into the depths of our solar system has revealed discoveries that challenge the possibility of life beyond Earth. Among the many celestial bodies orbiting our giant neighbor Jupiter, Europa is a world of special interest. With its jagged surface and hidden ocean, this icy moon has long intrigued scientists and dreamers alike. However, it's the recent discovery of JWST that's brought Europa into the spotlight of astrobiological research. JWST, in an unprecedented observation of the moon, has discovered carbon dioxide on Europa's surface. This discovery, while seemingly simple, has profound implications. Carbon dioxide, a molecule integral to life as we know it here on Earth, could be a marker pointing to the potential for life on extraterrestrial worlds. Let us together delve into the data obtained by JWST. What secrets does Europa hide beneath its icy facade? Could the discovery of carbon dioxide be a clue to life beyond Earth? Europa, a moon full of mystery, is a landscape both alien and fascinating. Its surface is covered in a canvas of ice with a complex network of lines and ridges. These features, known as lineae, are not just surface scars, but tell the story of the dynamic geologic processes taking place. This 9 to 15-mile thick ice shell hides a vast ocean that has interested scientists for decades. The lines on Europa's surface are believed to be the result of the ice crust interacting with the Moon's underground ocean. These cracks and ridges form as the ice shifts and breaks, a process driven by Europa's motion around Jupiter. Beneath this frozen barrier is a salty ocean, estimated to be 40 to 90 miles deep. This hidden sea, dark and cold, is kept liquid not by solar heat, but by Jupiter's immense gravitational pull. So-called tidal deformations. The satellite rotates around its giant parent and generates enough heat to maintain the ocean's liquid state. The chemical composition of this ocean is the subject of intense research and speculation. It's believed that there may be hydrothermal vents on the ocean floor, similar to those found in Earth's oceans. These vents may provide the necessary energy and minerals to sustain life, making Europa's oceans a prime candidate for the search for extraterrestrial life. The physical properties of Europa's oceans also raise intriguing questions. The presence of salts and the ability to form complex organic compounds, combined with the energy of hydrothermal activity, create an environment in which life can exist. Ocean depths and pressures, although extreme, are not beyond habitability, as evidenced by life in the deep gorges on Earth. Europa's mysterious environment with its icy surface and ocean is an interesting case for research. But what exactly has attracted the eyes of scientists to this moon this time? With the help of JWST, astronomers have made an interesting discovery. Using data from NASA's Space Telescope, they've detected carbon dioxide on the icy surface of the satellite. This discovery is not just an addition to Europa's chemical profile, it's an important key to understanding the moon's potential for life. Using the near-spec near-infrared spectrograph, JWST has discovered carbon dioxide in the geologically young and chaotic Terra Regio locality. This discovery is not just about the presence of a molecule, it's about its origin. The carbon dioxide on the surface of Europa is thought to have come from within, from its mysterious underground ocean, rather than having been deposited by external forces, such as meteorites. This discovery suggests a dynamic exchange between Europa's ocean and its icy shell. The most interesting thing here is that carbon dioxide is unstable on Europa's surface, suggesting constant replenishment from the moon's interior. The presence of carbon dioxide in the young terrain region indicates a recent and possibly ongoing process. This exchange may hold the key to understanding ocean chemistry and, by extension, its ability to support life. This discovery was made possible by the near-spec JWST instrument, which provided detailed spectra of Europa's surface. The ability to pinpoint the location of specific chemicals, such as carbon dioxide, allows astronomers to build a more complete picture of Europa's chemical landscape. Each discovery adds a piece to the puzzle of this mysterious moon. But why is this gas being released? And even more so, how does this cosmic body remain warm, supporting a liquid subsurface ocean? Europa, in its gravitational interaction with Jupiter, experiences a phenomenon known as tidal deformation, or tidal flexing. This process, caused by Jupiter's enormous gravitational pull, is one of the key factors in shaping Europa's potential to harbor life. As Europa revolves around Jupiter, its shape is constantly bending. This constant bending generates significant internal heat, a process quite different from the solar heating that we're familiar with on Earth. This internal heating is critical because it's thought to keep Europa's underground ocean in a liquid state, despite the relatively low temperature of outer space. The heat generated by tidal bends may also stimulate geologic activity on Europa, such as subglacial volcanism and hydrothermal vents. These openings, if present, may be similar to those in Earth's deep oceans, which teem with life despite the lack of sunlight. The energy provided by tidal bends could be a crucial ingredient for life. In Earth's oceans, hydrothermal vents support entire ecosystems where life forms utilize chemical energy released from the Earth's interior. On Europa, a similar process could occur, with life forms potentially using the energy from hydrothermal vents to power their metabolic processes. In such an environment, life could exist independently of sunlight, relying instead on the chemical and thermal energy provided by Europa's internal dynamics. Carbon dioxide, a molecule so integral to life on Earth, now takes center stage in the discussion of extraterrestrial life. On our home planet, carbon dioxide is the cornerstone of the biological process of photosynthesis that drives Earth's ecosystems. But what role can this essential molecule play in the cold, alien environment of Europa? The discovery of carbon dioxide on Europa by the James Webb Space Telescope opens up intriguing possibilities. In extraterrestrial environments, especially on icy moons like Europa, carbon dioxide may play a different but equally important role in sustaining life. In the absence of sunlight, life in Europa's oceans will have to rely on chemical energy, a concept known as chemosynthesis. This is where carbon dioxide can play a key role. In Earth's deep oceans, some organisms use carbon dioxide combined with hydrogen from hydrothermal vents to create organic matter. This process, although independent of sunlight, is a fundamental aspect of life in extreme environments. The presence of carbon dioxide on Europa may indicate a similar process. If there are hydrothermal vents in Europa's oceans, as many scientists believe, these may be the very places where life forms use carbon dioxide, perhaps like Earth's deep-sea organisms. This leads to an intriguing question. Could the carbon dioxide on Europa's surface be a byproduct of biological activity in its oceans? While the topic remains speculative, such a possibility adds an exciting dimension to the search for life beyond Earth. The role of carbon dioxide in extraterrestrial biological processes is the subject of intense research and speculation. Its presence on an icy moon may be a marker indicating the potential for life in environments far removed from the sunlit world we know. So let's summarize. The key to Europa's potential habitability lies in three basic elements: liquid water, an energy source, and the necessary chemical elements such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Europa's subsurface ocean and the energy generated by tidal bends are consistent with the first 2 points, and the presence of carbon dioxide on its surface hints at the presence of the necessary elements. Detecting carbon dioxide on Europa is an important piece of the puzzle. On Earth, carbon dioxide is integral to life, playing a central role in photosynthesis and respiration. In the alien environment of Europa, this molecule may be equally important, potentially acting as a building block or part of metabolic processes for hypothetical life forms. The presence of carbon dioxide also suggests that Europa's environment is chemically active, a key factor in the search for life. This activity could indicate geologic processes or even hint at biological processes if life existed there. It's also only possible to emphasize the importance of studying Europa's ocean as a testing ground for understanding the origin of life. The conditions on Europa may be similar to those of early Earth, giving a rough idea of how life could have originated under extreme conditions. On Earth, carbon dioxide is a fundamental component of life, involved in processes such as photosynthesis and respiration. In the alien environment of Europa, this molecule could play a similar role, potentially serving as a building block for life or part of the metabolic processes of a life form. Carbon dioxide could be a byproduct of biological activity or a resource. As we stand on the threshold of a new era in astrobiology, the significance of the discoveries of the James Webb Space Telescope propels us into a future rich with possibilities. Upcoming missions to Europa, particularly the European Space Agency's JWST, Jupiter Icy Moons Explorer, and NASA's Europa Clipper, are designed to broaden our horizons and deepen our understanding of this enigmatic moon. NASA's JWST mission, launched on April 14, 2023, aims to make detailed observations of Jupiter and its 3 large icy satellites, with a particular focus on Ganymede. However, the Europa survey will provide important data that will complement JWST's findings by providing insight into Europa's icy crust and its subsurface ocean. In turn, NASA's Europa Clipper, scheduled for launch in October 2024, is designed specifically to study Europa. Equipped with a suite of sophisticated instruments, this mission will conduct a detailed reconnaissance of Europa's ice shell and subsurface ocean in search of signs of habitability. The purpose of these missions is to build on JWST's groundbreaking discoveries, delve into the mysteries of Europa's environment. By scrutinizing Europa's surface, analyzing its ocean, and searching for biochemical signatures, these missions will improve our understanding of this moon's potential to support life. By the way, you still have a unique opportunity to be part of this historic exploration and get into the history of this remarkable moon. To quote NASA, join the mission and have your name engraved on NASA's Europa Clipper spacecraft as it travels 1.8 billion miles to explore Europa, an ocean world that may support life. Sign your name today to the message in a bottle. End of quote. Just imagine at a time when some people haven't even visited the next country, a piece of your personal history will travel such distances to orbit another planet. A truly mesmerizing thought. By adding your name, you're not just leaving a personal mark, you're becoming part of a legacy that will resonate in the annals of space exploration. Europa, once a distant and icy moon, is now the center of our quest to understand the existence of life beyond Earth. The JWST results, combined with future JWST and Europa Clipper studies, usher in a new era of astrobiology. An era in which the search for extraterrestrial life is moving from the realm of speculation to reality. In the vastness of our solar system, beyond the belt of asteroids and gas giants, lies a world shrouded in mystery. Neptune, the 8th planet from our Sun, a distant ice giant, has long captured our imagination. For decades, we've imagined it as a dark blue sphere at the edge of our cosmic neighborhood. But what if the vision of this distant world was an elaborate illusion? This mysterious planet, named after the Roman god of the sea, has hidden its true colors from us. Cloaked in a shroud of deep blue, Neptune has been the subject of many stories and scientific investigations. But recent discoveries have removed this azure facade, revealing a reality far more complex and fascinating than we could have imagined. For years, our telescopes have been pointed at this distant giant, capturing its essence in pixels and data. What we saw, however, was not the reality of the planet, but a reflection of our own technological and perceptual limitations. The deep blue color we associated with Neptune was actually the result of our own interpretations and enhancements, a story we unwittingly created and believed. Today, we invite you to explore Neptune like never before. Delve into its true colors, understand its dynamic atmosphere, and unravel the secrets of its moons and rings. For centuries, Neptune was portrayed as a dark blue world whose color reflected its cold, distant nature in the solar system. This representation, deeply ingrained in our collective consciousness, has become the cornerstone of our understanding of this icy giant. But what if this image was a reflection of our perceptions rather than the planet's true appearance? Neptune's color is a story of scientific evolution and the search for truth. It begins with the Voyager 2 probe launched by NASA in 1977. Sent to the outer reaches of the solar system, it took the first close-up images of Neptune, painting a picture of the planet awash in a stunning blue color. However, these images were not a direct window into the true color of Neptune. In fact, they were interpretations, the result of processing the data through the lens of human understanding and the technological capabilities of the time. The deep blue color we saw was the product of enhancements made by scientists to emphasize certain features of the planet. This story began to unravel with the advent of more advanced telescopes, such as the Hubble Space Telescope and the Very Large Telescope. These instruments, equipped with state-of-the-art technology, allowed astronomers to see the true color of the planet again. The results of this study were striking. The new images revealed that Neptune's color was not the previous deep blue, but rather a more muted and varied shade. This discovery was not just aesthetic, but a fundamental shift in our understanding of the planet. The reason for this color misconception lies in the way we process and interpret astronomical data. Colors in space images are often enhanced or altered to emphasize certain features or to make them more distinguishable to the human eye. In the case of Neptune, these enhancements over time have led to a collective opinion of its deep blue color. So, what led to this discovery? The key lies in a meticulous study entitled Modeling the Seasonal Cycle of Uranus's Color and Magnitude and Comparison with Neptune. This study, led by Patrick G.J. Irwin of Oxford University, along with a team of experts, set out to unravel the mysteries of Uranus's seasonal color changes. However, their journey will inadvertently shed light on the true colors of Neptune, disproving long-held beliefs. The team carefully analyzed a huge array of data obtained from Lowell Observatory over 6 decades. These data, supplemented by Hubble Space Telescope observations, produced a detailed picture of Uranus's disk-averaged color and photometric magnitude, revealing the complex interplay of its seasonal changes. One of the most important aspects of this study was the focus on the reflectivity of Uranus and the abundance of methane. The researchers unraveled a complex relationship between the lower methane content at polar latitudes and the different reflectivity of aerosol particles. This complex interaction of elements in the atmosphere of Uranus was thought to be influenced by the presence of methane ice particles, adding a new layer of complexity to our understanding. In parallel, the study allowed for a fascinating comparison with Neptune. Contrary to popular belief, the difference in blue hues between Neptune and Uranus was less pronounced. This discovery was the result of a critical reassessment of Neptune's color, disproving the image of deep blue that had been ingrained in our minds. The methodology used by the team was a combination of quantitative analysis, atmospheric modeling, and advanced spectroscopic observations. They converted measured reflectance spectra into radiance spectra, and then into tri-stimulus values. This process mimicked the visible colors of the planets as perceived by the human eye, bridging the gap between the raw data and our visual interpretation. The use of advanced telescopes such as Hubble and the Very Large Telescope played an important role in this endeavor. These technological marvels allowed the team to revisit and re-examine the true colors of Uranus and, by extension, Neptune, with unprecedented accuracy. As we delve deeper into the mysteries of Neptune, we find ourselves amid a maelstrom of atmospheric activity, in stark contrast to the relative calm of its stellar neighbor Uranus. Neptune's atmosphere, a turbulent and dynamic formation, is home to some of the most extreme weather in our solar system. One of the most striking features of Neptune's atmosphere is the presence of colossal storms, the most famous of which is the Big Dark Spot. Discovered by the Voyager 2 spacecraft in 1989, this massive storm, similar to Jupiter's Great Red Spot, is a testament to the turbulent nature of the planet. A large, dark spot, a giant rotating storm, is a window into Neptune's intense atmospheric dynamics. These storms are caused by the strongest winds in the solar system, reaching speeds of up to 1,300 miles per hour. However, to this day, the power and magnitude of these winds are a mystery to scientists, raising questions about their origin and the energy sources that drive them. In contrast, neighboring Uranus is a picture of tranquility. Its atmosphere, although composed of hydrogen, helium, and methane, does not have the same violent storms and extreme winds as Neptune. The difference in atmospheric activity between these two ice giants is one of the many mysteries of our solar system. Another intriguing aspect of Neptune's atmosphere is the presence of unusual hotspots, where temperatures can reach a staggering 750 degrees Kelvin. These hotspots represent a paradox because they exist on a planet so far from the Sun. The source of this heat remains a mystery, but theories suggest it could be caused by internal processes such as auroras or magnetic reconnection in the plasma layers. The origin of these hotspots and the extreme weather conditions on Neptune are the subject of ongoing research. They force us to seek new answers to questions about planetary atmospheres and hint at complex internal processes that have yet to be understood. Stepping outside Neptune's turbulent atmosphere, we enter a realm of celestial harmony where moons and rings swirl around this icy giant. Turning our gaze to Triton, Neptune's largest and most intriguing moon, we discover a world of seasonal changes and atmospheric mysteries. Triton, a unique moon with a retrograde orbit, was the last solid object visited by the Voyager 2 spacecraft during its historic journey through the outer solar system. Because of its retrograde orbit, indicating that it was captured by Neptune's gravity, Triton stands out among the moons of our solar system. Its surface, covered in nitrogen ice, is geologically young and active, with dark green streaks indicating the presence of geysers spewing nitrogen gas. Triton's thin atmosphere, whose thickness varies with the seasons, is a fascinating study in extraterrestrial meteorology. Observations with the European Southern Observatory's Very Large Telescope have revealed that Triton's southern hemisphere is in the height of summer. This distant moon, despite its relative distance from the Sun, is experiencing significant atmospheric changes. The heat of the summer sun causes the thin layer of frozen nitrogen, methane, and carbon monoxide on Triton's surface to sublimate into gas. This process causes the icy atmosphere to thicken as the season continues in Neptune's 165 Earth-year orbit around the Sun. The season on Triton lasted more than 40 years, and the southern summer solstice occurred in 2000. The discovery of carbon monoxide in Triton's atmosphere, as well as the confirmation of the presence of methane, marked a significant advance in our understanding of this moon. The presence of these gases, especially the enrichment of ice with carbon monoxide in the upper surface layer, feeds the atmosphere and determines its seasonal dynamics. These findings required a revision of Triton's climate and atmospheric models. The complex interaction of nitrogen, methane, and carbon monoxide not only determines atmospheric conditions, but also provides insight into the geologic and climatic history of the moon. But Triton is not alone. The planet is accompanied by a retinue of smaller moons, each contributing to our understanding of this distant world. These moons also show seasonal changes and provide insight into the complex gravitational interactions and environmental conditions around Neptune. When we turn our gaze from the moons to Neptune's rings, we encounter another aspect of this planet's mysterious nature. Neptune's rings, made up of a mixture of dust and ice particles, are dull yet mesmerizing. They testify to the planet's dynamic history. Scientists believe they're remnants of moons that were destroyed by collisions or torn apart by Neptune's gravity. The composition and characteristics of these rings are closely related to Neptune's true color and atmospheric phenomena. The subtle hue of the rings, which are affected by light scattering in Neptune's atmosphere, add another layer to the planet's color palette. The rings, reflecting and refracting light from the Sun, create the overall appearance of Neptune seen from afar. In 2022, the James Webb Telescope captured the clearest view of the rings of this distant planet in 30 years. Photographed with unprecedented clarity, these rings have changed the way we think about this distant planet. The most striking thing about the new Webb image is the clear view of Neptune's rings. Some of these rings, dim and dusty, have not been detected since the historic Voyager 2 flyby in 1989. The Webb telescope, with its enhanced capabilities, has brought these elusive rings back into focus. Neptune's rings are made up of several bright and narrow, as well as fainter dust bands. Infrared imaging by the Webb telescope has put these rings in a new light, revealing features that were previously hidden in the darkness of space. This is the first time these rings have been seen in the infrared spectrum, providing new insights into their composition and behavior. Neptune's rings, like the planet itself, are characterized by a unique composition. Unlike the gas giants Jupiter and Saturn, Neptune is an ice giant, rich in elements heavier than hydrogen and helium. This composition also reflected in the planet's signature blue color in visible wavelengths caused by a small amount of methane gas. In infrared images taken by Webb's NIRCam, near-infrared camera, Neptune does not appear blue, in contrast to the darkened appearance one would expect due to methane absorption of light. In infrared images taken by the Space Telescope, Neptune appears as a luminous, glowing white sphere. This absorption also affects the appearance of Neptune's rings, as they reflect and refract light traveling through the planet's atmosphere. This unexpected brightness in the infrared is the result of a unique interaction between the planet's atmosphere and infrared light. While methane gas absorbs red and infrared light, high-altitude clouds in Neptune's atmosphere reflect sunlight before it's absorbed. These methane ice clouds appear as bright streaks and spots that cast a ghostly glow on the planet in the infrared spectrum. By the way, you may wonder why Triton looks like a dazzling point of light adorned with shining spikes, as opposed to the more subdued image of Neptune. These diffraction spike patterns are a characteristic feature of the imaging telescope. They're not physical structures, but rather optical artifacts created by the telescope's design. Light from Triton passing through the mirrors and telescope structure is diffracted, resulting in these striking peaks emitted by the moon. Diffraction, in simple terms, is what happens when a wave, such as light, travels around the edge of an object or through a small opening. Imagine light in the form of water waves flowing through a narrow slit in a wall. When the waves pass through the slit, they diverge in different directions, instead of just going straight through. This propagation of waves after passing through a hole or around an edge is what we call diffraction. In the context of the James Webb Space Telescope and its images, diffraction peaks arise because of the way the mirrors and structure of the telescope are arranged. When light from a bright object, such as a star or Triton in images of Neptune, enters the telescope, it's bent slightly by the edges of the mirrors and other parts of the telescope. As a result of this bending, the light diverges and forms the star-like spikes we see in the images. The study of Neptune's rings, especially in the infrared, provides valuable insights into the atmospheric conditions and internal composition of the planet. The interaction of the rings with Neptune's atmosphere, particularly the methane ice clouds, provides insights into the planet's climactic and environmental processes. The bright equatorial band that girdles the planet hints at the global atmospheric circulation, a key driver of the planet's winds and storms. The atmosphere, which sinks and warms near the equator, glows more intensely in the infrared than the cooler gases that surround it. As we conclude our journey through the mysterious world of Neptune, we reflect on the impact these discoveries are having on the broader field of planetary science and exoplanet exploration. Neptune, once a distant blue spot, is now a testament to space exploration's dynamic and ever-evolving nature. Discoveries concerning Neptune's true color, its atmospheric phenomena, and the intricate details of its rings and moons go far beyond our solar system. They provide a crucial example for understanding similar ice giants and exoplanets in the far reaches of our galaxy. The insights gained from Neptune will help astronomers decipher the mysteries of these distant worlds and enrich our knowledge of the universe. As we continue to gaze into the cosmos, Neptune reminds us of the limitless potential for discovery. Its example encourages us to keep looking, asking questions, and unraveling the mysteries of the universe. In the 21st century, humanity finds itself at a crossroads at a moment in history when we can see the stars, but not yet touch them. Born in the era between exploring our own planet and the possibility of reaching other worlds, we stand on the threshold of an extraordinary journey. It's not just about rockets or physics, but about our survival and our place in the universe. Imagine a future in which Earth faces an existential threat, a catastrophic collision with an asteroid, a climate collapse, or something completely unforeseeable. Our solution? Build generation ships, colossal spaceships that serve as floating cities where multiple generations are born, live, and die while traveling to another star, to a new home. Einstein's special theory of relativity tells us that traveling faster than light is impossible. However, space is within our reach, even at a speed that is only a fraction of the speed of light. Generation ships traveling at a significant fraction of light speed could travel vast distances between stars. With technologies such as matter-antimatter engines, compact fusion drives, and even black hole propulsion, what seems like science fiction could become a reality. But these ships are not just vessels. They are lifeboats for humanity. They must sustain life for centuries, perhaps millennia, facing the challenge of space travel, genetic diversity, and mental health. Each ship will be a microcosm of Earth with its social structures, cultural heritage, and daily challenges. What would it take to build such a ship? How can its inhabitants survive and thrive? Join us as we delve into the intricacies of interstellar travel without exceeding the speed of light. Today, we'll try to unlock the secrets of how humanity can one day travel to the stars, but not in an instant, but through generations. Planning for interstellar travel is not only about technology, but also about predicting why such travel might become necessary. Foreseeable threats to humanity's survival may force us to seek refuge outside our solar system. Understanding these threats will help us prepare for possible future scenarios that could force humanity to embark on such an extraordinary journey. One of the most immediate threats comes from space itself: comet impacts. Throughout Earth's history, collisions with comets and asteroids have caused mass extinctions and major climate shifts. A strong enough collision could make Earth uninhabitable, forcing us to seek a new home among the stars. Another serious threat is climate collapse. Human activity has already led to significant changes in our climate: rising temperatures, melting polar ice caps, and increasingly severe weather events. If these trends are not controlled, Earth could become hostile to human life, making searching for habitable exoplanets a top priority. Technological progress, while bringing enormous benefits, also carries significant risks. Advances in artificial intelligence, biotechnology, and autonomous systems could lead to scenarios where humanity faces a threat from its own creations. Uncontrolled AI or engineered pathogens could become existential risks, leading to the need to establish human colonies on distant worlds as a defense of our species. In search of a new home, Proxima Centauri B is a prime candidate. Located just 4.24 light-years away in the Alpha Centauri system, it is the closest known exoplanet that's in the habitable zone of its star. As many know, this zone, often referred to as the Goldilocks zone, is the area around a star where conditions may be optimal for the existence of liquid water, an essential ingredient of life for humanity. Proxima Centauri B was discovered in 2016 and has been the subject of intense study ever since. It orbits a red dwarf star that's smaller and colder than our Sun, meaning the planet would have to be much closer to its star to be in a habitable zone. This proximity, while favorable for retaining heat, also exposes the planet to flares and radiation, which must be considered when planning human habitation. Current research indicates that the planet has a mass similar to Earth's and may have a rocky surface. However, much about it remains unknown, including the composition of its atmosphere and the presence of liquid water. Future missions and observations will be needed to collect more data and assess its suitability for life. Sending a spacecraft to our nearest neighboring star involves not only covering the distance, but also ensuring that the distance is suitable for human life. This requires a multifaceted approach that includes robotic probes and telescopes to gather detailed information about the planet's environment. These missions will help determine the feasibility of establishing a human colony and the preparations necessary for long-term survival. Proxima Centauri B was chosen as our target because of its relative proximity and potential habitability. However, reaching and inhabiting the distant world will be a monumental task requiring an unprecedented level of planning, innovation, and collaboration. The dream of exploring the stars has always been tempered by the harsh realities of physics and time. Traditional concepts of space travel, where one crew sets off and reaches their destination within their lifetime, seem increasingly impractical when it comes to the vast distances between the stars. This is where the concept of intergenerational ships come into play, a bold and innovative solution to the problem of long-distance space travel. Generational ships, also known as intergenerational or generation ships, are designed to keep people alive for centuries or even millennia. These ships are self-sustaining ecosystems with not only one crew on board, but all of their descendants. Life on a generational ship is designed to mimic a small self-contained world with living quarters, food production, water recycling, and social systems. The concept is simple, yet profound. As the original crew ages and eventually passes away, their children and their children's children continue the mission. This life cycle ensures that for many generations, the ship will continue its journey, and each new generation will be trained and prepared to maintain the ship and eventually reach its destination. This approach to space travel requires careful planning and robust systems to ensure that the inhabitants survive and thrive. Every aspect of life must be carefully considered, from genetic diversity to ensure a healthy population, to cultural and educational programs that preserve and pass on vital knowledge and skills. Einstein's special theory of relativity presents a serious problem for traveling faster than light. According to this theory, as objects approach the speed of light, their mass increases and they require exponentially more energy to continue accelerating. This effectively makes traveling faster than the speed of light impossible with our current understanding of physics. Generational ships offer a practical solution within the framework of Einstein's theory. By accepting the duration of space travel and planning for generations of life aboard such ships, humanity can aspire to distant stars. Such an approach recognizes the limitations imposed by the theory of relativity, while at the same time supporting the resilience and adaptability of the human spirit. Traveling to the stars requires overcoming significant challenges, not the least of which is the vast distance between celestial bodies. To make interstellar travel feasible within a human lifetime, we have to take a closer look at the advanced propulsion techniques and the intriguing phenomenon of relativistic time dilation. Relativistic time dilation is a consequence of Einstein's special theory of relativity. When an object approaches the speed of light, time on board is slowed down compared to the time experienced by an observer at rest. This means that for a spacecraft traveling at a significant fraction of the speed of light, the travel time of the crew will be shortened compared to those who remain on Earth. For example, if a ship could travel at 90% of the speed of light, time dilation would cause 1 year aboard the ship to be equivalent to more than 2 years on Earth. Because of this effect, interstellar journeys stretching over decades or centuries may seem shorter to the crew, although they do not shorten the actual distance. Several advanced propulsion methods have been proposed to achieve the high speeds required for interstellar travel. Each method has its own set of problems and potential advantages. For example, antimatter propulsion involves the annihilation of matter and antimatter with the release of enormous amounts of energy. This reaction releases energy much more efficiently than chemical rockets, potentially allowing spacecraft to reach significant fractions of the speed of light. However, producing and storing sufficient antimatter remains a major technical hurdle. On the other hand, compact fusion reactors use nuclear fusion, the same process that powers the sun to produce energy. By combining light atomic nuclei, such as hydrogen, with heavier nuclei, these reactors could provide sustained and powerful thrust for spacecraft. While controlled fusion technology is promising, it's still under development, and building a compact and reliable reactor suitable for spaceflight is another major engineering challenge. Black hole propulsion is a more speculative concept that involves harnessing the enormous gravitational energy of a black hole to propel a spacecraft. The idea is to create a small artificial black hole and harness the energy of the Hawking radiation it emits. Theoretically, this method could provide continuous and powerful acceleration, but the technology to create and control artificial black holes is still in the realm of something fantastic, far beyond our current capabilities. However, the problems don't end with thrusters. Traveling at near light speed is fraught with many dangers. One of the main ones is the threat posed by interstellar particles. At these high speeds, even tiny particles can cause significant damage in a collision. Spacecraft must be equipped with advanced shielding to protect against these high-energy collisions. Radiation is another serious hazard. High-speed space travel exposes the crew to intense cosmic radiation that can have deleterious health effects. Effective radiation protection and possibly even medical intervention will be a necessity to keep the crew healthy during long-duration missions. Maintaining the structural integrity of the spacecraft over the long term is also critical. The stresses and strains of high-speed flight can weaken materials over time, requiring advanced construction techniques and regular maintenance to keep the spacecraft safe and functional throughout the voyage. Despite these formidable challenges, the pursuit of interstellar travel drives human ingenuity and ambition. By researching and developing advanced propulsion techniques and overcoming the dangers of high-speed travel, we're taking crucial steps toward reaching for the stars and expanding our presence in space. Choosing the right propulsion system for interstellar travel is one of the most important decisions in mission planning. The propulsion system determines the speed, duration, and feasibility of the mission, so it's important to explore both best practices and traditional methods. One promising approach is to scale up the traditional propulsion technologies. NASA's Parker Solar Probe uses a combination of chemical propulsion and gravitational assists to achieve unprecedented speeds. The probe is traveling at more than 430,000 miles per hour. which is approximately 0.064% of the speed of light and makes it the fastest man-made object to date. Its propulsion system is based on hydrazine thrusters, powered by solar energy, which showed the potential of using existing technology for high-speed space travel. Gravitational assists, or slingshot maneuvers, use the gravity of planets or other celestial bodies to increase the speed of a spacecraft without expending additional fuel. By carefully planning a trajectory, a spacecraft can gain significant speed, reducing travel time over vast distances. This technique, while insufficient by itself for interstellar travel, can be an important component of a multi-stage propulsion strategy. Scaling up these traditional technologies involves developing more efficient thrusters and larger amounts of fuel. Another promising area is innovation in ion thrusters, which use electric fields to accelerate ions and create thrust. Ion thrusters are highly efficient and can operate for long periods, making them suitable for long-duration missions. The combination of these advanced conventional methods could be a practical solution for the initial stages of interstellar travel. For faster travel, we must consider more advanced propulsion methods, such as nuclear propulsion. One of the most intriguing concepts in this category is the Orion project, first proposed in the 1950s. This method involves a series of thermonuclear explosions behind the spacecraft, each of which creates a powerful thrust to propel the spacecraft forward. The Orion project uses a massive pusher plate at the rear of the spacecraft, designed to absorb shock waves from explosions and convert them into forward momentum. By repeating this process in a controlled manner, the spacecraft will be able to reach significant fractions of the speed of light, drastically shortening the flight time to nearby stars. Although the concept is theoretically sound, many technical and safety problems still have to be solved. Controlling the timing and directions of explosions requires precise design, and the spacecraft in turn must be designed to withstand enormous loads. In addition, the environmental impact of launching such a vehicle from Earth must be carefully considered, which may also require space launch platforms. Another fusion engine concept is the Daedalus project, which involves using fusion reactions to propel a spacecraft. This method involves the use of small pellets of fusion fuel, such as deuterium and helium-3, which are ignited by electron beams to create a constant thrust. The Daedalus project aims to reach speeds of up to 12% of the speed of light, which would make it possible to travel to the nearest stars within a human lifetime. Fusion propulsion offers a more controllable and potentially safer alternative to the Orion method. However, the technology to build reliable and efficient fusion reactors for spaceflight is still under development. Significant advances in fusion research and engineering are needed to make this approach viable for interstellar missions. Choosing the right propulsion system is a balance between feasibility, safety, and performance. Traditional methods, such as those used in the Parker Solar Probe, offer practical short-term solutions, while advanced fusion propulsion concepts such as the Orion and Daedalus projects promise the potential for faster and more ambitious interstellar travel. Ensuring the survival and health of the crew over multiple generations is a cornerstone of generational ship planning. One of the most important aspects is maintaining genetic diversity, which is necessary to prevent inbreeding and genetic diseases that could jeopardize the mission. To solve the problem of genetic diversity, scientists use Monte Carlo simulations. These models use statistical methods to simulate and predict genetic variability over many generations. By introducing various parameters such as initial population size, mutation rates, and reproductive patterns, these simulations can provide insight into the genetic health of a population over time. Monte Carlo simulations help determine the minimum population size needed to maintain genetic diversity and prevent inbreeding depression. may also take into account possible random events, such as accidents or disease, that could affect the population. Such modeling is essential to creating a sustainable human colony that can thrive for centuries. Maintaining genetic diversity requires careful planning of reproductive strategies and potential genetic screening. The crew must be educated about the importance of genetic health and the steps necessary to maintain it. This includes monitoring genetic diversity and making informed decisions about partnership and reproduction. Research shows that a minimum initial population of at least 100 individuals is required to maintain genetic health over several generations. This figure comes from studies by scientists such as Frederick Moran and Camille Belufi, who have extensively studied the genetic dynamics of small isolated populations. In their research, Moran and Belufi use Monte Carlo simulations to explore different scenarios, including different population sizes and reproductive strategies. Their study shows that with a balanced sex ratio and optimal reproductive rate, an initial population of at least 100 individuals can maintain a healthy gene pool. This population size ensures that genetic drift and inbreeding will not jeopardize the health and viability of future generations. An initial population of 100 individuals should grow to 500 individuals over several generations. This growth is necessary to create a stable and resilient population that can cope with unforeseen challenges. The modeling takes into account various factors, such as random genetic mutations, environmental influences, and possible catastrophes to ensure the sustainability of the population. Designing a generational ship to accommodate a growing population involves planning for adequate living space, resources, and social structures. The ship should provide educational, health, and recreational facilities to support the physical and mental well-being of the crew. And this includes collaborative activity spaces and private living quarters to provide a balance between social interaction and personal privacy. Beyond the physical infrastructure, it's vital to maintain social cohesion and cultural continuity. The crew must develop a shared sense of purpose and identity to foster cooperation and sustainability. Cultural and educational programs play a key role in maintaining the knowledge and values necessary for mission success. Effective crew and population planning is essential to the success of a generational ship. Using advanced genetic simulations and research, we can ensure that the population remains healthy and viable. With careful planning and a commitment to maintaining social and genetic health, humanity can thrive on the path to the stars, ensuring the survival and prosperity of future generations. Above all, however, designing a generation ship capable of sustaining human life for centuries involves creating a self-sustaining environment that mimics the basic aspects of life on Earth. This includes creating artificial gravity, producing food, and recycling vital resources such as water and air. These systems must be reliable, efficient, and able to operate autonomously for long periods. One of the most important aspects of ship design is the creation of artificial gravity to maintain the health and wellness of the crew. Prolonged exposure to microgravity can lead to muscle atrophy, loss of bone density, and other health problems. To counteract these effects, generation ships can use rotating media to create a centrifugal force that mimics Earth's gravity. The most practical design involves a large rotating ring or cylindrical section where the crew lives and works. As the structure rotates at a certain speed, centrifugal force pushes the occupants outward, simulating the effect of gravity. For example, a ring with a radius of 100 yards must rotate at a rate of about 3 revolutions per minute to create an artificial gravity of 1 g, similar to Earth's. This design not only helps maintain physical health, but also provides a familiar environment that can alleviate the psychological challenges of living in space. Rotating habitats can include living quarters, recreational areas, and workspaces designed to optimize the use of available space and resources. Reliable and efficient food production systems are also required to sustain populations for generations to come. Hydroponic and aeroponic systems offer solutions for growing crops without soil, using nutrient-rich water or mist to nourish the plants. These methods are highly efficient, use less water and space than traditional farming, and are well suited to the controlled environment of our ship. Hydroponic systems involve growing plants in nutrient solutions with their roots suspended in water. Aeroponic systems, on the other hand, use a fine mist to deliver nutrients directly to the roots. Both systems can grow a wide range of crops, from leafy greens to root vegetables, providing balanced nutrition for the crew. These systems can be automated and monitored to maintain optimal growing conditions, ensuring a stable and reliable food supply. In addition, genetic modification and breeding will be able to increase the yield and nutritional value of crops. Efficient water and air recycling is critical to the sustainability of a generation ship. Water recycling systems must be capable of recovering and treating wastewater, ensuring a continuous supply of clean water for drinking, cooking, and irrigation. Advanced filtration and purification technologies, such as those used on the International Space Station, are already achieving high levels of efficiency. On the ISS, for example, the water reclamation system can recycle up to 98% of wastewater, including urine and sweat. This level of efficiency is necessary for long-duration missions when resupply from Earth is not feasible. Ships of future generations will need to improve this efficiency even further, aiming for near-complete recycling to minimize the need for large water reserves. Air recycling is equally important, requiring systems that can remove carbon dioxide and replenish oxygen. Natural systems, such as photosynthesis in plants, can be integrated with artificial CO2 scrubbers to maintain a balanced atmosphere. Plants, in turn, not only provide oxygen but also contribute to the psychological well-being of the crew by providing a connection to nature. Projects such as Biosphere 2 have demonstrated the potential for creating closed ecosystems in which plants, humans, and microorganisms coexist by recycling air, water, and nutrients. Although Biosphere 2 faced some challenges, it demonstrated the feasibility of such systems, providing valuable lessons for the design of life support systems on generational ships. Creating a self-sustaining generational ship requires integrating advanced technology with natural processes to ensure the health and well-being of its inhabitants. Artificial gravity, efficient food production, and reliable disposal systems are the very pillars of this design, enabling humanity to embark on a long-term journey to the stars. Ensuring the success of a multi-generational mission goes beyond the physical and technological aspects of the ship. It requires meeting the mental, social, and educational needs of the crew, ensuring their health, motivation, and cohesion throughout the long voyage. Isolation and confined spaces can significantly affect morale and mental health. Lack of new stimuli and prolonged separation from Earth can lead to feelings of loneliness, depression, and anxiety. Addressing these issues is critical to maintaining a stable and motivated crew. Virtual reality technologies offer promising solutions for mental health and cultural connection. By creating immersive simulations of terrestrial environments, virtual reality or VR can provide a sense of escape and familiarity. Crew members will be able to see forests, oceans, and even social gatherings, helping to alleviate feelings of isolation and to maintain a connection to their home planet. Artificial intelligence can also play an important role in supporting crew mental health. AI therapists, such as NASA's Simon 2.0, can offer individual counseling, monitor psychological well-being, and suggest strategies for coping with stress and interpersonal conflict. These AI systems can adapt and learn from each generation, providing continuity and consistency in mental health support. Ensuring the intergenerational transfer of knowledge and skills is critical to mission sustainability. A comprehensive education system must be put into place to ensure that each new generation receives the necessary skills to operate and maintain the ship, as well as the knowledge to continue research and exploration. This should include formal education, practical training, and the preservation of cultural and historical knowledge. Embarking on an interstellar voyage requires not only technological prowess, but also a deep commitment to the human spirit. By addressing the mental, social, and educational needs of the crew, we ensure the resilience and connection of each generation that carries the torch of exploration and survival. Advanced technologies such as virtual reality and artificial intelligence support, combined with strong cultural and social structures, will create the foundation for a thriving community across generations. When we reach beyond our solar system, a harmonious blend of innovation and humanity will lead us to new worlds, securing our future as an interstellar species. In a universe filled with mysteries, one question towers above many others. Are we alone? This riddle, also known as the Fermi paradox, attempts to answer our understanding of the cosmos and our place in it. Named after physicist Enrico Fermi, who during a casual dinner conversation reflected on the silence of the universe. The paradox confronts us with a stark contrast. On the one hand, the sheer number of stars, like grains of sand on Earth's beaches, suggests a high probability of extraterrestrial civilizations. On the other hand, our sky remains eerily silent, devoid of any sign of these civilizations. Despite advanced technology and the ever-expanding reach of space, not a single whisper or wave has reached us from deep space. This silence raises profound questions. What are the barriers that prevent potential civilizations from reaching out or crossing the stellar expanse? Can the vast distances of the universe or the fleeting nature of civilizations explain their absence? Or does the answer lie in the very fabric of the emergence and survival of life in space? Among a sea of stars, our solar system provides a glimpse of the possibilities and limitations of life beyond Earth. Ice moons and distant worlds harbor oceans beneath their frozen crust, mirroring the early conditions in which life is thought to have originated on our planet. These hidden oceans, protected from the harshness of space, may be the cradle of life and intelligent beings. However, these creatures may very likely be incapable of traveling beyond their icy boundaries, or even unaware of such a possibility. Just such a hypothesis was recently proposed, forcing a rethinking of the variables of the Fermi paradox. Let's take a closer look at how much it's affected the answer to why we still have not been able to hear the echoes of alien civilizations in the universe. The silence that reigns in space is an enigma that has baffled minds for decades. Imagine a universe where technological marvels and interstellar communications fill the void between the stars. Such are the expectations of our science fiction and logical predictions based on the Drake equation, which estimates the number of active, sociable extraterrestrial civilizations in the Milky Way galaxy. However, when we delve into the vastness of space, the reality is strikingly different. The expected intergalactic discourse remains only an expectation. The Fermi paradox asks a deceptively simple question. There are billions of stars in the galaxy, many of which have Earth-like planets. But where is everyone? This fact has definitely caused perplexity among scientists and the public alike, leading to numerous theories attempting to solve this mystery. One common explanation is the Great Filter Theory, which suggests that at some point in the evolution from a planet to intelligent life capable of colonizing galaxies, there is a highly improbable step that few, if any, civilizations overcome. On the other hand, the zoo hypothesis, suggests that advanced extraterrestrial beings deliberately avoid contact with us to allow for natural evolution and socio-cultural development, much like zookeepers observing animals in a sanctuary. Strangely, despite our sophisticated antennas and listening devices, we've still not picked up the slightest whisper from space. This leads one to speculate that perhaps our listening techniques are not adapted to alien communication methods. Or worse, that intelligent life is extremely rare or short-lived due to self-destruction or cosmic events. Especially given the vast expanse of space we've already scanned, it's hard to draw any other conclusions. Why is this happening? It may suggest that our knowledge is incomplete now, or we're listening in the wrong way and at the wrong time. However, perhaps things are much simpler than they seem. One recent intriguing proposal is the fishbowl worlds hypothesis. The traditional search for extraterrestrial life often focuses on Earth-like conditions, planets in the habitable zones of their stars, with liquid water and atmospheres capable of supporting life as we know it. However, such a view can be too narrow and fail to take into account life that does not meet our Earth-like expectations. The fishbowl worlds hypothesis proposes a radical shift in the search for life. According to it, life thrives in subsurface oceans completely enclosed by a thick layer of ice. These worlds offer a stable environment protected from cosmic hazards such as radiation and meteor strikes, favoring the development and evolution of complex ecosystems in isolation. This theory draws inspiration from the work of scientists such as Alan Stern, whose contributions to space exploration have shed light on the mysteries of icy celestial bodies in our solar system. For example, the New Horizons mission discovered intriguing features on Pluto and its moon, Charon, that suggest the presence of subsurface oceans, as well as the possibility of similar conditions even in the colder regions of the Kuiper Belt. And in general, our solar system has moons such as Enceladus and Europa, orbiting Saturn and Jupiter, respectively. Geysers spewing water vapor and ice particles into space observed by instruments such as Cassini hint at a dynamic, active environment beneath their icy crust. But how do these icy moons and dwarf planets affect the fishbowl worlds theory? Well, the key lies in understanding the complex interplay of gravitational forces, radioactive decay, and perhaps even hydrothermal vents on the ocean floor, all of which may contribute to the creation and maintenance of subsurface oceans. In such an environment, life as we know it, or even life forms beyond our current understanding, could find a way to thrive, isolated but protected from the harshness of space by a thick layer of ice. In these secluded ecosystems, life could thrive without the ability to gaze at the stars or contemplate the universe beyond their icy confines. This begs the question, how could such isolated creatures communicate, or even imagine a reality beyond their own? This fact is definitely puzzling because it shatters our preconceived notions of what an advanced civilization might look like. On this basis, we can assume that the universe may be teeming with life hidden in such natural shelters. Perhaps our galaxy is full of these quiet, isolated worlds, whose inhabitants unknowingly share the cosmos with us. Beneath the icy shell of distant worlds, the concept of communication takes on a new dimension, far removed from our earthly perceptions. In these hidden oceans, life forms can develop unique methods of communication that are profoundly influenced by their secluded environments. On our planet, the ocean depths provide a glimpse of how life can adapt to the perpetual darkness of the subsurface. Marine species such as whales and dolphins use sound to communicate over vast distances of up to several thousand miles, a method that's efficient and effective in the dense environment of water. This terrestrial analogy suggests that creatures in the hidden oceans of icy worlds may also rely on sound or other forms of non-visual communication, negating the need for technology such as radio signals. In the absence of light, these creatures could have developed advanced echolocation abilities similar to those of cetaceans on Earth, allowing them to see through sound. Knowledge acquisition in this context would be fundamentally different, potentially focusing on nuanced acoustic information rather than visual or electromagnetic signals. It's quite possible that these mysterious beings, thriving in their secluded worlds, have a deep understanding of their environment, yet remain ignorant of the cosmos around them. However, the vast universe, with its myriad worlds, presents not only opportunities for life, but also formidable challenges for civilizations seeking to reach the stars. Among these challenges, the gravity of home planets is a colossal barrier to the dream of interstellar exploration. This aspect introduces another critical factor into the Drake equation known as the exoplanetary escape factor, which assesses the feasibility of space travel from worlds not like our own. Exoplanetary escape factor is an important addition to the Drake equation, offering a method for quantifying the difficulties an extraterrestrial civilization might face in trying to escape the gravitational grip of its home planet. The equation for the escape velocity of a planetary object shows that larger and more massive planets pose a huge problem. Earth, whose escape velocity is 11.19 kilometers per second, serves as a baseline for comparison. For instance, a hypothetical super-Earth with a mass much greater than our own would have a prohibitively high escape velocity, making conventional space travel an insurmountable task. Imagine the scale of engineering and energy required to break away from a planet far greater in size and mass than Earth. Escape velocity from such worlds would be much higher, requiring propulsion systems far beyond our current capabilities. Such worlds may be rich in life and even have advanced civilizations, yet remain eternally isolated and their skies eternally out of reach. These civilizations may develop in complete ignorance of the cosmos, and their technological advances limited to the confines of their own world. However, it is conceivable that these civilizations could explore alternative routes into space. Innovations such as space elevators, orbital rings, or even harnessing the energy of planetary rotation could provide solutions to the difficult problem of high flight speeds. However, these technological advances will require materials and energy sources far beyond what we currently consider possible. In addition, it further complicates the version about the development of life on icy moons and dwarf planets. Enclosed in a thick ice shell, these worlds provide protection and stable conditions for life, but they also create additional layers of isolation. For intelligent beings living in such environments, the very concept of space may be incomprehensible, hidden behind impenetrable barriers of ice and rock. It begs the question, how would these creatures perceive their place in the universe? And what colossal effort would it take for them to break through the ice ceiling and venture into the unknown? It would be logical to assume that in the heart of a world bound by the heavy chains of gravity or by a dense shell, the pace of life and the trajectory of civilization follow a lesser-known path. Here, the attention of intelligent life forms would be visibly directed inward, toward their world. In such societies, environmental constraints may lead them to focus on mastering their immediate surroundings, optimizing their habitat, and exploring their world in depth. In such a case, there's nothing strange about their lack of connectivity. Being able to go beyond their planet is necessary for the concept of going into space to be a foreign idea, both figuratively and literally. Now, as we stand on the threshold of a new era in space exploration, our eyes are turned not only to distant stars, but also to the icy guardians of our own solar system. Several ambitious missions will be heading to this icy expanse in the coming years. Europa Clipper, scheduled for launch this October, targeting Jupiter's moon Europa. Dragonfly, planned for a 2028 departure to Titan. And several proposed concept missions targeting Saturn's moon Enceladus are at the forefront of this search. These celestial bodies, once considered frozen wastelands, are now seen as prime candidates for the search for extraterrestrial life in our solar system. These missions are equipped with advanced technology to penetrate ice sheets and explore the vast oceans beneath them. By analyzing the composition of water plumes ejected into space, studying the geology of the ice, and mapping the subsurface oceans, scientists hope to find signs of life, or at least the conditions necessary for it to exist. In any case, so far, there's no direct evidence of extraterrestrial life in our system. However, in the next decade, this veil will be opened and will shed new light on this issue. The data collected may provide empirical support for the idea that life can exist in conditions far different from those on Earth, and that the universe may be teeming with invisible life, much of it hidden in such isolated fishbowl worlds. However, if we find nothing, we may have to scrap the idea and start looking elsewhere for clues. One thing is clear: our search, whether it uncovers vibrant alien ecosystems or stark voids, will forever change our cosmic perspective, propelling us into the next chapter of human discovery. Saturn has captivated the human imagination. From ancient civilizations to modern astronomers, the Maori of New Zealand, separated by vast oceans and without telescopes, somehow knew that Saturn had rings. How? The mystery deepens. Saturn has long been a symbol of the unknown and mysterious. Its iconic rings have been the subject of wonder and speculation since the time of Galileo. But what if we told you that these rings, however eternal they may seem, are actually a fleeting cosmic phenomenon? Adding to the intrigue is a storm twice the width of Earth, with a mysterious hexagonal shape that's raging at Saturn's North Pole. What forces could have created such a geometrically perfect formation? But the mysteries don't end there. Saturn's satellites, Titan and Enceladus, offer conditions that could potentially support life. Lakes of liquid methane and geysers spewing water and organic material into space make these satellites more than just celestial bodies. They're potential homes for life. Join us for a closer look at this enigmatic giant and its cosmic mysteries. Our journey begins with Galileo Galilei, the Italian astronomer who first pointed his telescope at Saturn in 1610. What he saw puzzled him, a planet with something like ears. He didn't realize he was looking at the edges of Saturn's magnificent rings, a feature that would puzzle astronomers for centuries to come. Galileo's telescope was primitive by today's standards, and the true nature of Saturn's ears remained a mystery. It was not until 1655 that Christian Huygens, armed with a more advanced telescope, correctly identified them as a system of rings surrounding the planet. Moving into the modern era, we witness the Pioneer 11 mission, the first spacecraft to fly past Saturn in 1979. This mission provided us with the first close-up images of the planet and its rings, revealing intricate details that were once inaccessible to Earth's telescopes and us. But it was the Cassini mission that truly revealed Saturn in all its glory. Launched in 1997 and arriving at Saturn in 2004, Cassini spent 13 years studying the planet, its rings, and its satellites. From discovering plumes of water ice on Enceladus to capturing the ethereal beauty of a hexagonal-shaped storm at Saturn's North Pole, Cassini revolutionized our understanding of this distant world. And here's an interesting point. Long before the advent of telescopes, the Maori people of New Zealand had myths that described Saturn as having a parero, or belt, around it. How they knew this remains a matter of debate and speculation. But as we'll see later, Saturn holds more than one mystery. What do you think could have created a hexagonal storm with an area larger than the Earth itself? Saturn harbors a geometric enigma at its North Pole, a six-sided storm that's puzzled scientists for decades. This six-sided wonder is not just a superficial feature, but a deep and enduring mystery that breaks down the understanding of fluid dynamics and planetary atmospheres. The hexagon was first discovered in 1981 by the Voyager spacecraft. But it wasn't until the Cassini mission, which orbited Saturn from 2004 to 2017, that we got a front-row seat to this cosmic spectacle. Cassini's high-resolution images showed a symmetrical jet stream surrounding the hurricane-like vortex at the center of the hexagon. Unlike Earth's chaotic weather systems, Saturn's hexagon is a masterpiece of geometric precision. So what's causing this hexagonal storm? Researchers at Harvard University have developed a 3D model that suggests deep thermal convection in Saturn's outer layers may be the culprit. This model shows that the storm could spread thousands of kilometers deep into Saturn's atmosphere, well beyond what we can see. Interestingly, scientists have been able to reproduce the hexagonal pattern in a laboratory setting. Although these experiments do not capture all the nuances of Saturn's complex atmosphere, they provide a glimpse of extraterrestrial phenomena. Saturn's hexagonal vortex contrasts sharply with Earth's polar vortex, which is irregular and less stable. This difference raises questions about the fundamental properties that distinguish the atmospheres of the gas giants from the Earth group planets. The longevity of the hexagon is another mystery. It's been observed for at least 4 decades, and possibly much longer. This steady feature suggests that everything that feeds the hexagon is not a temporary phenomenon, but a stable, perhaps even permanent, aspect of Saturn's internal dynamics. Let's shift our attention from the mystery of the hexagon to another wonder of Saturn. Saturn's rings are more than just celestial jewelry. They're dynamic, ever-changing systems that interest astronomers and the public alike. But what are these rings made of, and why are they so short-lived? Saturn's rings are composed mostly of water ice with a mixture of dust and rocky material. They range in size from tiny particles to huge chunks the size of houses. These ice particles are not static. They're in constant motion under the influence of Saturn's gravity and the gravitational pull of its satellites. The rings are divided into several subdivisions and gaps, each with its own unique characteristics. Most notable are the A, B, and C rings, separated by gaps, such as the Cassini ring, a gap 3,000 miles between the A and B rings. The origin of Saturn's rings has been the subject of debate. One popular theory suggests that they formed from the remnants of a shattered moon. Another theory states that they're the remnants of material from the formation of the solar system, captured by Saturn's gravitational pull. Recent research has also shown that the rings may be much younger than Saturn itself, perhaps around 400 million years old, based on the rate of dust contamination. Saturn's rings don't last forever. They're slowly disappearing because of a phenomenon known as ring rain, in which ring particles are drawn into Saturn's atmosphere. This process is accelerated by micrometeoroid bombardment and interaction with Saturn's magnetic field. At the current rate, some scientists predict that Saturn's rings could disappear within 100 million years. The depletion of the rings would not only change Saturn's appearance, but could also have consequences for its atmosphere and magnetic field. As for a moment, we realize that even the most fascinating features of our universe are not immune to the inexorable forces of physics, doomed to disappear into the chronicle of eternity. Saturn, the ringed giant of our solar system, is not just a celestial wonder. It's also a cosmic playground that contains some of the most intriguing satellites, 2 of which, Titan and Enceladus, have fascinated scientists and sparked debate about the potential for life beyond Earth. Titan, Saturn's largest satellite, is a world shrouded in mystery. Its dense atmosphere is rich in organic compounds, and there are lakes and rivers of liquid methane on the surface. But what's truly amazing is Titan's rate of removal from Saturn. 100 times faster than previously thought. amounting to a staggering 4.3 inches per year. This rapid drift suggests a dynamic and evolving relationship between Titan and Saturn. Could this drift affect Titan's internal dynamics? And perhaps even its potential for the existence of life? An atmosphere rich in organic compounds such as nitrogen and methane, and the possibility of an underground ocean, make Titan a tempting target for the search for extraterrestrial life. But the question remains, what would life look like in an environment so radically different from Earth's? And let's remember Enceladus, another satellite of Saturn that's very different from Titan. It's an icy world with a highly reflective surface that outshines any other body in the solar system. Enceladus takes the concept of an ocean world to a new level. Not only does it have a subsurface ocean, but it also sprays it into space, where samples of it can be collected by a space probe. This ocean contains most of the chemical ingredients necessary for life, including hot, mineral-rich water erupting from hydrothermal vents. Hydrothermal vents can provide the necessary conditions for life as we know it. On Earth, these vents are teeming with life forms that thrive in extreme conditions. Could Enceladus's vents be home to similar but alien life forms? Enceladus also contributes to Saturn's E-ring, a unique characteristic that further enriches the dynamic relationship between the Moon and its host planet. The icy particles in this ring open a window into the Moon's internal chemistry, providing clues that may reveal its secrets. Titan and Enceladus are two moons orbiting the same planet, but quite different in their characteristics. Both present compelling arguments in favor of the potential for life, fueling our curiosity. As we ponder the possibilities of life on Saturn's satellites, it's worth noting that our curiosity is not limited to telescopes and computer modeling. Upcoming missions aim to study these satellites up close and perhaps answer some of our most pressing questions. Meet Dragonfly, NASA's ambitious mission to Titan. Scheduled for launch in the 2030s, this rotorcraft will fly over Titan's diverse terrain, from dunes to impact craters. Dragonfly's main goal is to search for the building blocks of life. It will analyze complex organic compounds in the atmosphere and on the surface, providing invaluable data on Titan's chemistry. Equipped with a suite of scientific instruments, Dragonfly seeks to understand the geologic processes on the Moon and how they relate to its potential for life. Could Titan's unique chemical composition and liquid methane cycles offer a different recipe for life? Although no missions to Enceladus are currently planned, the Moon's potential for life has made it a prime candidate for future exploration. Scientists are proposing missions that could fly through Enceladus's plumes and directly sample its underground ocean. Such a mission could analyze the chemistry of the plumes in search of signs of life or prebiotic chemistry. The presence of hydrothermal vents in Enceladus's oceans adds another layer of intrigue, suggesting an environment in which life could potentially thrive. Despite the technical challenges, a mission to Enceladus could revolutionize our understanding of the potential for life in the solar system. It could provide direct evidence for the existence of extraterrestrial life, or at least provide clues to the conditions necessary for life to exist. As we mentioned, Saturn's rings don't last forever, as we once thought. Recent studies have shown that a process that can last hundreds of millions of years is causing these icy wonders to slowly fade away. But what significance does this have for Saturn and its complex atmospheric dynamics? According to a study by the Japan Aerospace Exploration Agency, this material, composed mostly of water, causes a decrease in electron density in Saturn's atmosphere. This phenomenon, known as ring rain, significantly affects Saturn's atmospheric conditions. Ring rain is not just a trickle. It's a stream that carries away water in amounts equivalent to an Olympic-sized swimming pool every half hour. Compounding the mystery is the relative youth of Saturn's rings. Although Saturn itself is about 4.6 billion years old, data from NASA's Cassini mission suggests that the rings may be only a few 100 million years old. This leads us to wonder, if Saturn's rings are so young, what catastrophic event could have led to their formation? Was it the destruction of a moon? Or perhaps the capture of a passing comet? Cassini's Space Dust Analyzer has added another layer of complexity. Over 13 years, it's collected 163 dust particles that came from outside the Saturn system. Surprisingly, the rings turned out to be quite clean, suggesting that they hadn't existed long enough to accumulate excess cosmic dust. This cleanliness raises the question, if the rings are young, why haven't they collected more cosmic dust? The absence of cosmic dust in the rings challenges our understanding of their age and their interaction with the wider cosmic environment. It's as if the rings are in a cosmic laboratory room or clean room, isolated from the dust that permeates the rest of the solar system. As the rings are depleted, Saturn's appearance will undergo a dramatic transformation. These rings have been the planet's hallmark. Their disappearance would not only change Saturn's appearance, but could also have unknown consequences for its atmosphere, perhaps even affecting the planet's albedo and heat retention. The loss of the rings could have a cascading effect on Saturn's atmosphere, potentially altering wind patterns and even affecting the planet's iconic storms. The full extent of these changes is still unknown, making them a subject of intense scientific interest. Interestingly, the fate of Saturn's rings may be inextricably linked to its satellites. Some theories suggest that gravitational instability may have destroyed some of the icy satellites orbiting Saturn, providing enough material to form the rings. Saturn's rings and satellites are like partners in a cosmic dance, each affecting the other in subtle but significant ways. As we continue to study these celestial bodies, we can say unequivocally that the fate of one can shed light on the mysteries of the other. Humanity stands on the threshold of a new era, an era defined not only by exploration, but also by the bold dream of colonization. For decades, our gaze has been fixed on the familiar, the Moon, our celestial neighbor, and Mars, the red beacon in our night sky. These worlds, once the subject of science fiction, now beckon us with the promise of new frontiers. But beyond these well-trodden paths lies a world shrouded in mystery, a world that's changing our understanding of what it means to be a moon. This is Titan, Saturn's largest satellite. Titan is a world covered with a dense atmosphere, which is rare for a moon. It's a place where rivers and lakes flow not with water, but with liquid methane and ethane. Here, the sky is raining gasoline, and the cold is beyond anything that can be experienced on Earth. Yet, in this alien landscape lurks the potential for something extraordinary. Could Titan, a world so unlike our own, hold the key to our future in space? Could this distant moon hold the secrets to not only surviving, but thriving beyond our home planet?
It's one small step for man, one giant leap for mankind.
As we turn the pages of our history of space exploration, the Moon and Mars become beacons of human ambition. The Moon, our nearest celestial neighbor, has always been a constant companion in our night sky, a symbol of our desire to leave the confines of the planet. Mars, in turn, with its striking resemblance to Earth, fuels our dreams of finding a new home in space. Nevertheless, the Moon, despite its proximity, presents serious problems. Its surface is a barren wasteland, devoid of atmosphere and offering no protection from the harshness of space. The lunar environment is a vacuum, exposing astronauts to extreme temperatures and cosmic radiation. No atmosphere means no air to breathe, no wind to carry sound, and no sky to protect against the relentless barrage of solar and cosmic rays. Mars, though more Earth-like, is not without its own problems. Its thin atmosphere, consisting mostly of carbon dioxide, offers little protection from solar and cosmic radiation. The Martian environment is harsh and merciless, and temperatures at the poles can drop to minus 257 degrees Fahrenheit. The lack of a global magnetic field exposes the surface to the full force of the solar wind and cosmic rays. In contrast, Titan, Saturn's largest satellite, presents a very different environment. Shrouded in a dense atmosphere, Titan offers a natural barrier against the dangers of cosmic radiation. This atmosphere, richer in nitrogen than even the Earth's atmosphere, is the key to protecting future colonists from cosmic rays that mercilessly bombard less protected worlds such as the Moon and Mars. Titan's atmosphere isn't just a shield, it's a gateway to opportunity. Unlike the Moon and Mars, the air pressure on Titan's surface is 1.5 times higher than on Earth, creating a surprisingly familiar pressure environment for human explorers. This dense atmosphere opens up new possibilities for exploration and colonization, possibilities that are beyond the reach of our more trivial space goals. As we rethink our goals for space colonization, Titan becomes a compelling alternative, a world in which the atmospheric and radiation problems that limit our ambitions on the Moon and Mars become its strengths. Titan invites us to envision a future in which humanity can thrive under the protective embrace of an alien sky, a future in which the mysteries of this distant moon become stepping stones to our expansion into space. As we mentioned earlier, Titan, a moon of many mysteries, orbits around Saturn. Discovered in 1655 by Dutch astronomer Christian Huygens, Titan has captivated the imagination of scientists and dreamers ever since. This world is both similar to and in stark contrast to our Earth. Titan's environment is unlike anything else we've encountered in our solar system. It's the only known moon with a dense atmosphere, and the second largest moon in our solar system after Ganymede, a satellite of Jupiter. But it's not just the size that makes Titan stand out, it's the rich composition of its atmosphere and surface that really sets it apart. This moon is surrounded by a thick, nitrogen-rich atmosphere, similar in composition to Earth's, but far denser and more extensive. It's permeated with organic molecules, creating a kind of hazy orange glow that obscures the surface of the satellite from view. It's this nitrogen-dominated atmosphere that provides protection from solar radiation, which contrasts sharply with the barren sky of the Moon and Mars. Beneath this alien sky lies a landscape at once familiar and utterly alien. Titan's surface is formed by rivers and lakes, but they're not bodies of water as we know them. Instead, they're filled with liquid methane and ethane, flowing through channels carved into the Moon's icy crust. These hydrocarbon seas are a true marvel, a testament to the diversity of the universe's chemistry. The presence of these surface fluids is a key characteristic that distinguishes Titan from other celestial bodies. On Earth, the water cycle shapes climate and geography. On Titan, a similar cycle occurs, but the role of water is played by methane and ethane. This hydrocarbon cycle, with methane rain and ethane lakes, creates a dynamic environment that may provide clues to understanding the complexity of planetary atmospheres. So, by breaking the limits of our standard perception, we're slowly uncovering exactly what makes a planet or moon habitable. Its nitrogen-rich atmosphere and surface fluids open the door to new possibilities. Let's find out what they are. So the Moon's nitrogen-rich atmosphere provides a natural barrier against cosmic radiation, a major challenge for space colonization. Why do we pay so much attention to solar radiation? Well, the answer is simple, yet profoundly important. Solar radiation is a ruthless destroyer of living cells. It doesn't just affect microscopic life forms, it directly affects us as human beings. Unshielded exposure to solar radiation can cause severe cellular damage, destroying the very fabric of our biological existence. In space, spreading uncontrollably, this radiation poses one of the greatest threats to the survival and health of astronauts. On Earth, it's the atmosphere and magnetic field that protect us. On Titan, it's the dense nitrogen atmosphere that provides vital protection, making it a safer haven for future human colonists than the barren landscapes of the Moon or Mars. Beneath this protective dome is a world of liquid methane and ethane. These hydrocarbon lakes and rivers stand in stark contrast to the bodies of water we know on Earth, yet they offer intriguing possibilities. Imagine a world where boats sail on methane seas, where the familiar concept of the liquid cycle takes on a whole new form. The presence of these surface fluids is not just a curiosity, it's a resource. Methane and ethane have the potential to be used as fuel, providing energy for future colonies. This abundance of hydrocarbons makes Titan an attractive target for colonization, offering a solution to one of the biggest problems of space habitation: sustainable energy sources. But Titan's gifts don't end there. Beneath its icy surface lies another treasure: water ice. The very water so essential to human life is abundant on the satellite, trapped in its frozen crust. The presence of water ice, along with hydrocarbons, makes this moon a repository of vital resources, setting the stage for a self-sustaining human presence away from Earth. Titan, a world of incalculable potential, also presents enormous challenges. Severe cold, during which temperatures drop to -356 degrees Fahrenheit, creates an environment unsuitable for human life as we know it. In turn, methane rain, a phenomenon unique to this moon, adds another layer of complexity to the survival equation. To overcome these challenges, we must turn to the pinnacle of human ingenuity and technology. Colonizing Titan will require not just adaptation, but a complete rethinking of human habitation in extreme conditions. Imagine dwellings designed to withstand low temperatures, insulated with materials yet to be invented, and harnessing the power of Titan's own resources to provide warmth and comfort. These habitats could be equipped with systems to convert atmospheric methane into heat, turning the problem itself into a resource for solving it. But survival is more than just keeping warm. Methane rain, while an obstacle, could turn into an advantage. Advanced collection and filtration systems could recycle methane not only as an energy source, but also as a raw material for essential commodities. Now, let's imagine a human colony on Titan. Imagine domed cities, their architecture a blend of science and art, designed to harmonize with Titan's unique environment. These structures, resistant to cold and methane rains, would be interconnected, forming a network, demonstrating human resilience in the face of alien conditions. Inside these domes, life thrives. Hydroponic gardens provide food, recycling systems conserve resources, and public areas foster a sense of community. It's a place where humanity has not just survived, but flourished, adapting decisively to Titan's challenges. Colonizing Titan is not just a distant dream. It's a future that beckons us to take up the challenge. With each technological breakthrough, with each bold leap of imagination, we come closer to making this alien world a new home for humanity. Watching the thriving human colony on Titan, it becomes clear that this moon is more than just a new home for humanity. It's a center of economic and scientific opportunity. The unique environment and abundant resources offer unprecedented prospects for both. The economic benefits of colonizing Titan are rooted in its vast hydrocarbon reserves. Key components of Titan's lakes and atmosphere are not only potential sources of energy, but also valuable raw materials for chemical synthesis. The ability to harness these resources could turn Titan into an economic center, meeting both the colony's needs and potentially supplying materials for interplanetary trade. Scientifically, Titan is a gold mine. Its complex atmosphere and surface chemistry offer unique research opportunities that offer insights into organic chemistry and astrobiology. Studying Titan's methane cycle and its prebiotic chemistry could unlock the secrets of the origin of life, not only on Earth, but potentially throughout the cosmos. Moreover, Titan's position in the solar system and its resources make it an ideal launching pad for future space exploration. Its low gravity and abundant fuel reserves could make it easier to launch spacecraft to distant destinations, making Titan a strategic outpost for exploring the outer solar system and beyond. However, with these opportunities come important ethical considerations. As we embark on the colonization of Titan, we must reflect on our responsibilities in interacting with the new world. Conservation of Titan's environment, respect for its unique characteristics, and thoughtful stewardship are paramount. We must approach Titan not as conquerors, but as custodians. How we relate to this world in the future will reflect our values and our ability to balance progress and responsibility. As we conclude our journey, let's reflect on the key points. A moon once shrouded in mystery has turned out to be a world full of potential. We explored the protective properties of Titan's nitrogen-rich atmosphere, a natural shield against the dangers of cosmic radiation. We traveled through alien landscapes where rivers and lakes of methane and ethane cut through icy terrain, offering resources that could secure our future in space. Our journey also took us to the potential of a vibrant human habitat, where ingenuity and resilience have turned challenges into opportunities. We saw how Titan's economy, driven by its abundant resources, can be a cornerstone of our interplanetary endeavors. As we ponder the future of humanity on Titan, we're reminded that colonization is not just about achieving technological perfection. It's a journey that forces us to grow, learn, and respect the universe we live in. So we leave you with a great question. What does this step mean for the future of humanity? How will our efforts on this distant moon affect our destiny in the vast, uncharted expanse of space?